recording now. Okay, so just again, just a warning. The session is being recorded. Please be mindful and respectful of the class environment and your fellow students. Anything you say, type, draw will forever be recorded with your name attached to it. So please conduct yourself in a professional manner and keep this top of mind. All right. So I've received all of your, most of them. I think there's a couple outstanding. So I'm just waiting to mark the last few. I'll have the results for the second submission by the end of this week, hopefully before Friday. Today I want to have a discussion regarding the servicing requirements for the gravity sewers, sanitary and storm. We'll look at the standards, and then we'll look at the information that we have as a starting point to do our detailed design of the new sewers. Okay, so we'll do some exercises related to the existing sewers, and then we'll look at the proposed. Okay, I want to start with the sanitary sewer. So I'm going to I'll share my screen. So the entire screen here. So we're going to look to the region of Halton standards to begin with. You probably covered the storm and sanitary design flow calculations in MPT last semester, and you may already be discussing it with Professor Neruzzi this week or next week as far as the requirements. I'm just going to go through some of the bare bones minimum details that's required, a little bit about the spreadsheet. So we're actually giving you a blank spreadsheet that you have to program yourself to calculate these things, but it's still worth going through the calculation at least manually once so you can see what it is you're up against. Okay, so I'm going to do some hand calculations. If you want to follow along, I suggest you get a notebook and a pen or a pencil. Have your calculator handy. You can help me with the calculations, so you can double check these. And these hand calculations will actually help you program the spreadsheet. Okay, and the checking exercise we're going to do for some of the existing sewers is going to help you program the spreadsheet and check it for any possible programming errors. Okay, and I'll demonstrate that as well. So for the sanitary sewer, we look to the region of Halton for the standards. Again, this is a document that you can tell it's a scanned image. Right? If you go through the first few pages, you can actually see the 3-ring binder hole punched on the side. So it really is just a scanned document, a hard copy. But with the software, at least that I'm using for Adobe, you can actually Control F, find stuff based on the character recognition. So I'm going to look at wastewater, not water. Okay, so we're looking to the wastewater system, right? So the first section, part A, is for the water system, the water main. We're looking at the wastewater system. So that starts in section A. Okay, so this is all water system. So this is section A. We're going to look to section B for the wastewater. Okay, so here's where the wastewater system information starts. So you can see here the table of contents and so on. Again, this should be a review for most of you. Maybe you haven't used the Halton standards, but the formulas should look very familiar. Okay, the first thing we need to look at is how we calculate the design wastewater flow. So section B2.1. This is the calculation or the formula or the procedure for calculating the expected wastewater. Okay. The wastewater is based on 3 parts. There's the average dry weather flow, this thing here, based on population. There's the average peak wastewater flow factor, the peaking factor, that's also based on the population. And then there's this infiltration allowance, which is really just a recognition that the pipes aren't perfectly sealed. So there's always either some groundwater during a rainstorm or a groundwater in a high water table that actually gets into the pipe system. So there's a little bit of inflow or leaking into the pipe system, which we allow for. Because that'll reduce the capacity of the pipe. So if we account for it, then we can appropriately size the pipe to account for that. So these are the 3 basic parts of the calculation. If you look at the requirement for the average dry weather flow, we're looking at a residential subdivision. So it's the table below, table B2.1, residential dry weather flow. And we're looking at, remember the different population densities, right? Single family, 55 persons per hectare. If it's a townhouse unit, it's 135 people per hectare. So these are the factors that help you determine the population in each of the areas based on the type of development, the residential type of development. But if you look at the unit or sewage flow, it's based on the population. So once you have the population, you know the number of people, you can see the sewage flow or the expected flow based on how many cubic meters per person per day or cubic meter per person per second is produced as wastewater. And they're all the same, right? A person is a person. Okay? The density changes based on the land use type, but once you have a population, you apply the per person unit rate. Okay? So we'll be using mostly this value here, right? So many cubic meter per person per second as a flow. Okay, that flow then needs to be have a peaking factor associated with it. So if we look on the next page, here's actually, these are the unit flows for commercial and light industrial areas, hospitals and so on. Okay, but we're doing residential, so it's the previous table, 2B21. The peak wastewater flow, again, there's a couple. There's one for commercial, part B, one for commercial and light industrial. We're looking at residential and community services use. So this is the formula here. You may recognize this from your previous classes, sometimes called the Harmond peaking factor. And it's just a function of the population. Okay? And if you were to plot that, you'll find the peaking factor is based on the population, but P, the value P, is in thousands. Okay? So if you have 1,000 people, P is 1 for this formula. You have to divide by 1,000, right? Population in thousands. And you'll notice as the population increases, right, you're increasing the denominator on this fraction. As the bottom value increases, the peaking factor decreases. And this addresses the idea of peak usage or peak flow times. If you think about a smaller township or a small developed area where the population mostly works in a given industry. Think about like a small town that has a paper mill. There are related shifts at the plant. So people are kind of getting up and going to work and coming home at the same time. So there's a peak flow in the morning, there's a peak flow in the evening. So as the population is smaller, you'll find that peak is a lot higher with a smaller population. As the population gets larger, a city like Toronto, say, as the population gets bigger, the peaking factor actually goes down because of the diverse types of industry and jobs that people have. So then you have a more average, stable usage of the sewage system, right? So not everybody starts at the exact same time. Not everybody comes home at the exact same time. You know, we have essential services that are 24-hour shifts. People working from home at odd hours. So there's all kinds of things that would really reduce the peaking factor. So as a general trend, as the population is small, you get a higher peaking factor. And as the population gets larger, you get a greater variety of work patterns. So the peaking factor starts to decrease. Okay, and that's the general idea. So you would take this factor and multiply it by the dry weather flow per person, and that's your flow. The last thing to look at is infiltration, and the infiltration is simply a rate. So we're looking here under B24, and they tell you it's 0.286 times 10 to the minus 3 cubic meters per second for every hectare. And that's why we're delineating areas in hectare on our drainage area plan for sanitary. Okay, so simply, I'm going to go to a hand calculation for the sanitary. I just got some notes here. So the design flow for sanitary, okay, is going to include 3 parts. You're going to see the average dry weather flow, so many cubic liters per second per person, right? Then you're going to multiply by a peaking factor, which is that formula for M, the Harmond peaking factor, and then we're going to add infiltration, okay? And that's the general idea. So you'll use that formula or that idea to calculate and to program the spreadsheet. So I'm going to give you a spreadsheet that's got it looks like a title block, but all the cells are blank. So you have to put in the input information and you have to calculate all the values. And I'll show you on the spreadsheet which values are typed in and which values should be calculated. Okay, so you can follow along and use the spreadsheet to to its full potential so that you can minimize the calculations you have to do. Okay, so the average dry weather flow for the residential neighborhood is actually 0.003183 times 10 to the minus 3 cubic meters per person per second. That's right out of the standard. The peaking factor, which we call M, right? The formula for M is 1 plus 14 over 4 plus the square root of P, where P is in thousands. All right, so you have to take your population and divide by 1,000. So that's the next part of the equation. And then finally we have infiltration, which is just a constant rate. Infiltration is equal to 0.286 times 10 to the minus 3 cubic meters per hectare per second per hectare. It really doesn't matter how you write it, per second per hectare. Okay. So at the end of the day, we do this. We take this times the peaking factor plus the infiltration. And that's how you calculate your expected flow. Okay, so that's the general behavior of sanitary flow. There's an average dry weather flow, right? So much usage by each person, right? So many cubic meters per person per second is going to be used on a daily basis. Then there's a peaking factor, which takes into account how big the population is. And then finally the infiltration, which is that kind of groundwater seeping into the pipe, which takes up capacity, so we have to allow for it. And it's been generally decided that that's the rate. That's how many cubic meters per hectare is going to sneak into the pipe, right? So we have to account for it. Any questions so far? Okay, again, a bit of review. You may have seen a similar calculation with a different standard. Does anybody recall, did you use an actual municipal or regional standard last semester, or did you just study this as a general formula? These are actually the region of Halton standards. Did you use a municipal or a regional standard in MPT, or did you just use a generic formula? Do you remember? Anybody want to share what you learned last semester? Generic, okay. So this is the general sense, right? Dry plus times peak plus infiltration. And these are the values used in Halton, which is the region that the town of Milton finds itself in. Okay. Any questions so far? This should be review for most of you. Okay. And again, for the sake of the third online quiz, right? You want to be able to cite where this information is coming from. That's why I'm showing you the document, right? If we go back to the Halton standards, the peaking factor comes from the design criteria. So the infiltration comes from the design criteria for the wastewater systems region of Halton B24. The peaking factor comes from residential. So B23 part A is the residential peaking factor. And then if you look up here on table B21, you'll see the residential dry weather flow per person, cubic meters per person per second. Okay, so you need to know where all this comes from. You remember the first, have you done your second quiz yet, your second test, online test? Or is that this week? Not yet, okay. When is it, this week? I think it's scheduled next week, okay. Monday, okay. So you kind of get the idea of what the expectations are on those tests. I don't prepare those, Professor Naruzzi does, but I have a pretty good understanding of what he's been doing. Again, that used to be an actual oral discussion. Every student would go in and sit with him face to face, and he would ask you those questions in person. Now he's kind of put it online and made it, I think, a multiple choice kind of a quiz. So it's just to make sure that you're reading the document. And once you learn how to read the standard, we worked in CDA. I taught you a little bit about the town of Richmond Hill. When you navigate the town of Milton standards, you'll see a lot of similarities, right? The details are a little different, but the kind of information you're looking for is very much the same. What's the minimum slope? What's the maximum slope? What are the K values for the roads? What's the curb return radius, and so on. So these are pieces of information that you need, and then depending on which municipality or region you're working in, the details may be a little different, right? But certainly if you can navigate the standards for one municipality or one regional government, at least you know what's in them. And when you see another region or town standard, at least you know what you're looking for, even if you don't know the values of what you're looking for. You know where to look or what to look for. So that's why we kind of put you through this. It's a real world exercise of reading through the document and finding what you need to do your work, right? So you have to be able to navigate these types of documents. And the online test is really just, making sure that you read through the document. Everybody kind of has to understand how to navigate these documents. It'll set you up good for work because you'll be dealing with different municipalities. Like I worked always in the GTA. I worked for firms in Markham mostly, but we did projects all over Southern Ontario. And some people in our office and I had been involved in a couple. I've done work across Canada for certain clients, and for the same company, I actually spent a couple of weeks. I was down there in person and then worked on some other projects remotely for Phoenix, Arizona. So I was in the United States, and I had to read their standards. In the United States, where there's no frost, where the ground doesn't freeze like it does in Ontario, the standards are quite different, right? But you're still looking for similar information all the time. What's the minimum slope on a road? How do you size your sewers? What's the average, sewage flow, and so on. So you know what you're looking for. It's just a matter of navigating through the document and knowing that there's a document to go by. There's a standard somewhere. Okay, so can I go on and go through some of the details for sanitary flow? I'll show you my drainage areas and my calculations. We'll talk a little bit about Civil 3D and the pipe database again. You remember what we did in CDA last semester? So we'll look at that as well. And I'll discuss specific to this project how I want you to approach the design for the sanitary sewer. Okay, any questions? Okay, so let me go on. I'm going to go back to, I'm going to get rid of my handwritten notes there. That's recorded now if you ever want to see that again. Okay. All right, so let's look at the drawing a little bit, and then we'll look at the design sheets. We have some PDFs from the previous subdivision, so we'll look at those as well. I've got a copy. You should all have a copy of this document here. You would have received this in MPT last semester. Does this look familiar? Table 1, capacity and discharge values for circular pipes. And then this proportional depth chart. This looks familiar? Okay. So I'm going to talk about this, but I don't want you to use this information exactly as you see it. Right? I'm showing it to you just for familiarity perspective, right? This is the kind of information, but I want you to calculate it using formulas. So when it comes to the capacity of a pipe and the velocity of a pipe flow, I want you to calculate it using the formula. So I'm going to review Manning's equation for Q and V. Okay, so we'll get to that in a little bit. But certainly you can always check your calculations against what you see here. All right. The one thing I won't have necessarily, and I'll leave it up to you if you want to use it or if you want to program it yourself, this table here, determining actual velocity from percent full, right? How much of the pipe is actually full. Okay, so we'll get to this. Does this look familiar when you have to calculate actual velocity? I hope. This is the chart you would use. I'll show you how I do it, which is basically a digital version of this. And then you can decide how you want to do it. Okay, so I just want this here. This is when you learned this, it wasn't a waste of time, right? This is kind of what we need to do next. So I'm going to go to the sanitary design sheet. This is a document. Okay, this is a PDF. It's available online. It is for the subdivision. You remember the subdivision external to ours, right? So if we go back to the drawing, right? Not what we're doing, but everything else, the entire subdivision surrounding us. So this is the sanitary design sheet for the entire subdivision. There are 5 PDF pages. If you go to the second to last one, not the last one, but second to last, 4 out of 5. If you zoom in here, you'll see Chuchmak. Okay, so there's Chuchmont Crescent. And Chuchmont Crescent has two sewers on it. It goes from manhole 56A to 57 and then flows from 57 to 58. Okay, so this is the design sheet for those two sewers. Now the reason I'm discussing this, and we're going to do this together, I'll show you what I want you to do and what I want you to check, but I will do it for us in class together. Okay, what I want to look at is, and I'm going to bring up my sanitary drainage area plan. So on the sanitary drainage plan, okay, if you zoom in here, so these are my drainage areas, and let me get rid of some of the other noise, right? We shouldn't see any grading, we shouldn't see any water main information, we shouldn't see any water main, we shouldn't see any storm, we should just see the water main and the road. Okay, keep it simple. So this would be the drainage area plan. Here's a common mistake on your drainage area plans. Notice I turned off or I froze everything that is not sanitary. You have to remember to do that for the existing stuff here, right? So there's a water main here. I hope you turn that off on your assignment. Turn this off, turn the sidewalk off, turn the water main, storm, back a curb, and make sure all the existing information that is not sanitary is also frozen or off when you plot, right? So this is what the sanitary plan should look like. You should see nothing related to storm, nothing related to water, nothing related to grading. Okay, there's some dimensions here that you can get rid of. Okay, so that's what the drainage area plan should look like. All right. So for my two sewers, the existing sewers here, I actually digitized. I'm going to show you here these two areas from the PDF. Okay, and I'll show you where I got that information from. We'll go to the drawings. So under Seneca MED sanitary drainage areas, right? I digitized these two areas here. So there's an area tributary to the sewer that goes from 56A to 57A, and there's an area that's tributary to this other pipe on Chuchmont that goes from 57A all the way to 58A. Okay, and on the design sheet, you'll see that. Okay. So 56 to 57, 57 to 58. So this stuff here, I'm going to highlight it. This information is typed in. Right? You read the drawing, decide what the maintenance hole number's in. We'll talk about numbering system in a moment. But that information is typed in. The length, this one here, comes from the drawing. Now you have a couple of options. You can just measure the length from the CAD file. So if you want to get that length, you could just, we drew a line, right? We have lines for the sewers. You could measure the length of the pipe, right? 74 meters. And this one here is 148. That might be too long. Might be the wrong one. Hang on a second. Sorry, this sewer here is 148. So let's just check here. Yeah, 148 meters. So that distance, whoops, that distance is actually from the CAD file, right? It knows the distance between the maintenance holes. So those numbers, whether you list it, do we also need to create these drainage boundaries? No, you don't. No, I just want to show you, I want to relate it to our work. Okay? So I know the length of this pipe and I know the length of this pipe from the drawing. You can get it by listing the line that you drew, or you can wait until you digitize the system. Remember when you trace the polylines with the database for the pipe network, and then the label of each pipe will actually annotate and show you the actual dimension or the length of the pipe. So you've got a couple of options. You can just list the pipe and get the length from AutoCAD, or you can digitize it, and I'll show you that today. Digitize the pipe system, and then you get a label that gives actual length, and you can read it from the drawing. Whatever method you choose, however you get the length, you then have to go to the design sheet and type the length in. So everything I've highlighted, you have to type. That's something you have to input into the sheet. Okay. The areas now come from your drainage areas, right? So 0.64 and 0.89, that comes from the drawing, right? 0.64 and 0.89, that comes from the drawing. And then based on the density, you have the populations, 87 and 121. So back to the drainage sheet. This information here is typed in, and this information is typed in. So these are all, whoops, these are all typed in values. Okay, so everything I'm highlighting, you physically have to type the value in yourself. Okay. Then when it comes to the totals, right, if I had different area, and you can see here the different types, right, single family, semi-detached, townhouses, commercial, school, and infill, you can get the areas. This column here, the total, is the sum of these columns, total area, right? And you're going to use the total area for each pipe to calculate the infiltration that's expected. Okay, so those are calculated values, and I'll show you on a spreadsheet, right? I just want to discuss it. Same thing here with the population, right? This population, you can type it in. I'm going to show you something a little different on the spreadsheet, but you can type it in by hand, or you can calculate it based on the math you have to perform, right? So if you take 0.64 times 155, right? 0.64 hectares, sorry, times 135 should give you 86 point something. We always round up 87. Okay, so you can read these from the drawing based on the math you did to produce this information, or you can calculate it again and verify what you typed into the drawing in the first place is correct. Okay, so there's a couple of ways of doing that. I'm going to do a little bit of both, but certainly those values have to be typed in or calculated. I usually calculate them, but I'll show you what I'm talking about when we get into it. Then there's the total, right? So what's the population in the first pipe? That's calculated. And what's the population in both pipes now? Because the next pipe in the system has to take the flow from the previous pipe plus the flow from the current pipe. So the total population. So as you move downstream, right? Let's go back to the drawing. Whoops. Go back to the drawing. The way we calculate this, there's a certain flow generated that gets into this pipe. Okay? The flow that gets into the next pipe is actually the entire population. All of those people are contributing to this pipe here, and so on. So it's a cumulative thing, right? What's the flow in this pipe? Well, the area and the population that's tributary to it. What's the flow in this pipe? Well, everything that comes from the tributary area for this pipe, everything upstream. So it's the sum of these two that you use to design this pipe downstream, and so on. Okay. How do you design this pipe? Well, you take the sum total of this, the sum total of this, and the sum total of everything coming from the north, and you design this pipe, and so on and so on. Okay, so it's a cumulative thing. And that's what the spreadsheet's going to help you manage. So you have to calculate the expected information per area or per pipe, and then on each pipe, recognize that there's flow coming from a previous pipe that's upstream. Okay, and that's part of the design exercise. Make sure that you accumulate the flow properly. So if you go back to the design sheet, you'll see that happening, right? So the first pipe on this area is a dead end, right? There's nothing else. This is the first pipe at the top end. So whatever this population is, it has a certain tributary flow to calculate the flow in this pipe. And then to calculate this, you'd calculate the population contribution from its tributary area plus this piece that's coming from upstream, this piece here. So let's look at the design sheet, right? So the population for the first pipe is 87. The population for the next pipe is 87 plus 121. The upstream population plus the current pipe's population. And that's how you get this total here. Okay? And again, I would use the spreadsheet calculations to get those values. All right. So these values highlighted, and I'm just looking at this one street, right? I mean the same for the whole table. These numbers you have to type in. Everything else on the sheet can be calculated up to this point here. Okay? Then, and what you calculate is up to this point, the maximum flow. This is the projected flow. Right? You calculate everything up to this column here. This is the expected flow in that's going to be produced by the area. Everything after this, where it says sewer, this is your actual sewer sizing. Okay, so let me show you on a spreadsheet. I should have it here somewhere. I believe it's on my desktop. So for the sanitary sewer, I've started to recreate that information. Okay, so I'm going to show you on my spreadsheet. Put it here so I can see the chat in case somebody has a question. Remember, you can always unmute yourself if you have a question. So what have I input here? I typed these numbers in. I'm just going to grade them so you can remember. I typed those numbers in. Do something a little lighter. Type those numbers in. I typed these numbers in. I typed, now these numbers here, I actually calculated them, right? So they're on the drawing, so I could type these in, 87 and 121. They're on the drawing. right? So I could take the population of 87 and 121 and just type them in based on the bubble data that I see here, or as a double check, this is what I like to do. I like to take this, and if you look at the spreadsheet, it actually gives you all the different densities. So for this, I actually take the area times the townhouse people per hectare. And if I double click here, you'll see the formula, right? I take 0.64 times 135 gives me the population. Now, if you do that, and let me show you off to the side here, this is equal to the area times the density. There's how many people. 86.4. There's no such thing as a fraction of a person, so you always round up. So what you can do in the spreadsheet is there's a formula for that. Instead of using the calculation, you can actually use a function called round up, up, and calculate the value, and it'll always round up. And it wants to know to how many decimal places, so comma 0, no decimal places. So then it rounds it to 87. It'll round up. So there's the programming that you might want to consider. The nice thing about this is if you calculate it on the spreadsheet, you can double check what you drew in the drawing. Is 87 correct? Is 121 correct? And so on. So you can double check your calculations. Whatever you typed into the drawing, you can use the spreadsheet to double check that. So I like to do that, but I always use the rounded form. I use the roundup function with 0 decimal places, right? It'll round up to the next whole number. Okay. The other thing is if you want to make a copy of this, right? So if I didn't calculate this and I want to calculate the next one, I'm going to make a copy, Control C. When I paste it here, make sure that you're referencing the correct cells. So if I double click here, you'll see it's picking up the new area, right, for the townhouses, but it's still using the 135. And the reason it's doing that is because if you look at the formula carefully, see these dollar signs, this dollar sign and this dollar sign? Those dollar signs make sure that when you copy, Control copy, I'm going to paste here. If I double click, it moves down the column to the next townhouse area, but it does not move down the column with the townhouse density. And that's what the dollar signs do here. Okay, so it's just a little bit of a lesson in using Excel. Okay, let me show you without what happens, right? So if we take out those dollar signs, if I just reference this with this number here, right, no dollar signs, watch what happens if I take this and I copy and I paste. So now if I double click, you'll see I went down 3 cells, right? So now instead of referencing this cell, it's going to reference this cell, right? So it goes down, but it also goes down here. I don't want to do that, right? And if you do this, you always have to lift this back up. And that's how it does the calculation. So to prevent the referencing from changing on the one cell that's always fixed, in this case the density, and you might be using this density for some, you want to put in the dollar signs. Fix the column and fix the row so that it always goes to that cell, no matter how many times you copy this. Copy this down this many times. You'll watch here, right? This number is always coming down because there's no dollar signs, right? So when I double click here, you'll see it's always following the row for where the formula is, but this is always fixed. And that's what the dollar signs do. Okay, so just some advice. Again, if you just want to program each one and, you know, reference the cell, the same number that you have to use all the time, I don't care how you do it as long as the calculation is correct. But these are some functions that you might want to make use of. The round up and the dollar signs for fixing the cell reference. Okay, so if you didn't know that, it might be a good tip. For the design sheets, do you want to see our formulas to get the values, or is it fine just to input the values? I want you to calculate everything using formulas in the spreadsheet. So I want your Excel file. That's the submission. Okay. So again, for reference, anything that I highlight in gray should be typed in by hand. Everything else should be a formula. Okay. So the design ends right here. So what else do you have to type in? Well, you have to type in the size and the slope. So this is manually typed in. What's the size of your pipe? What's the slope of the pipe? And then calculate Q using a formula, calculate V using a formula, calculate the actual velocity. This is the only thing here that you might want to do manually, if you're not sure. This you might want to do manually using this information. Okay? So you might want to do this manually and then type it in by hand. Okay? But I have a slightly different way of doing it with a lookup table. I'll talk more about that later. This is also typed in. This is just the pipe material and the class. Okay, so this is actually typed in as well. Okay, every other number that's not highlighted is calculated. Okay, again, with the exception of this. You could type these in or not. I'll leave that up to you, right? But this is the sum of this entire row, and this is the sum of the next row for area and so on. And this is cumulative. It takes the previous area plus the current area, right? So 64 plus 89 is 153. So it takes the previous total plus the sum of all the pieces for the current pipe. Okay, this population, same thing. This is the population for the first pipe. This is the population for the next pipe plus the previous pipe. So the previous total plus the sum of the pieces for this pipe as well. So that's cumulative. All right, and then the next few columns actually calculates the flow for the dry weather flow, the peaking factor, and then filtration. Okay, so here we go. Let's do this. So for the incremental flow, this thing here, this is the dry weather flow. You'll see here, right, there's that factor that we talked about earlier, 0.3183 times 10 to the minus 3. That number comes from the standard, which is this number right here, right? Just take this and multiply by negative 10 to the negative 3, so add 3 more zeros after the decimal place. So that's where this number comes from. And it's based on that flow times the population, how many people. So every person uses this much cubic meters per second. So this times the incremental flow, right? So this is per person multiplied by the number of people. Okay, so that's where this comes from. The next one, again, is looking at the total flow in the next pipe, which is the accumulated population times that factor. Right, so now we have this population, which is the previous plus the current, times the same factor. Okay, but now you're looking at the total population up to that point. So that's why this is the sum. So that calculates. And 16 is the total flow, 208 times the factor. Okay. So there's your dry weather flow, and it's accumulating, right? You're adding it up as you go down the pipe system. Okay. The total flow now. Right, the total flow now is the previous flow. The total flow now is the previous flow. It's the sum of this flow plus this flow, which I think is a bit of a mistake. Let me just check that. 3, 4. Oh no, so this is 4, 7. Okay, so let me just check that. Yeah, so this is based on. Oh, sorry, this is based on the 121. Sorry, it's based on the 121. N16. Yeah, so it's based on just this population. Sorry, so this is the flow in this pipe, and this is the flow in the next pipe. In the next column, we start to accumulate it. So now we take the previous flow plus the current flow gives you the total flow. My mistake. So this is actually the previous flow plus the current flow is the total flow. So we're accumulating here, not here. Okay, so you can see this plus this equals this, right? 003 plus 004 is 007. Okay, let me zoom in on that. Okay. So this is based on 87 people, and this is based on 121 people. And then it's the sum. So this can be calculated by adding this plus this, which is what I'm doing. Or you could actually take the flow factor, times the total population. So if I wanted to do this just as a guide, copy, just so you can see what's happening, I can paste this and reference the total population and get the same answer, 0007, right, if you round it. Whoops. Right, so that's where this is coming from. So you can get the flow for this, get the flow for this, that's what these two are, and then accumulate them, add them together here, or you can calculate it as a total population. I won't be able to tell the difference, but whatever you do, make sure that you use a calculation. Don't type it in. Don't do it on paper and then type it into the spreadsheet. Okay? You're not using the power of the spreadsheet to its full potential. All right, so that's the accumulated flow. So this is per pipe, and this is accumulated flow, dry weather flow. Then we're looking at the peaking factor. Now you're looking at an accumulated population. So this peaking factor is based on this population. right? And there's that formula, right? Take the population, divide by 1,000, square root. So that's the Harmon equation for M. The next one uses the total population, right? And you can see the peaking factor is starting to go down because the population is going up, okay? So this is the dry weather flow accumulated. This is the peaking factor accumulated. And then in the next column, you simply multiply this times this to get this. This times this to get this, and that's all there is to it. Multiply them together. So that's the first part of the equation. Dry weather flow times the peaking factor. And the last thing to worry about is infiltration. How much water is seeping into the system? How much do I have to account for? Because you lose capacity. If there's groundwater getting into the pipe, then there's less room in the pipe for the flow, the expected sanitary flow, so you have to account for that. So in the infiltration calculation, you'll see it's based on 0.286 times 10 to the minus 3, or divide by 1,000, times the area. Okay, so it's going to be referencing the area, the total area, up to that point. And then this one is the accumulated area, so it's going to look at the sum of the two areas. So that's this one here. It looks at the sum of the two areas. And then for each pipe, you have the dry times peak plus infiltration. Dry times peak plus infiltration. And that's all this does. It adds up these two columns. So 12 plus 2 is 14, 27 plus 4 is 32. Now it looks like it's there's a bit of a rounding issue, right? 27 plus 4 is actually 31, but we're looking at 4 decimal places, it's rounding. So there's a bit of a rounding issue, but it should work out. And what you want to do is check this. What I want you to do is type in these formulas and make sure you get the same numbers on the spreadsheet that are on this PDF, right? 3, 3, 4, 7, 4, 2, 6, 4, 14. And if I'm doing the math right, I should get the exact same numbers. If you don't, you have to check your formulas. Excuse me a minute. Excuse me. Sorry about that. Had to sneeze. All right. So there's a good way of checking whether you've programmed this correctly, right? Once you program this correctly, then you can cut and paste one cell into another and make sure that the reference is correct. Okay, so everything up to this point here, let me zoom out a little bit. Right? Everything up to this point here, right? All of this stuff is calculating the expected flow. Everything on the other side is calculating an appropriate pipe size that can accommodate that flow. So this is your flow determination. What's the expected flow based on people and peaking factor and so on. And then on this side, we now look at the capacity and velocity of a pipe and make sure that the capacity of the pipe is greater than the expected flow. Okay, so that's the second part of this. Any questions so far before I get into the pipe calculations? So let me zoom in here. So now what we want to look at is, this is how much flow is going to get into the first pipe. Okay, so many cubic meters. If you multiply by 1,000, you get liters per second. So 1.4 liter per second. And the next pipe is an accumulated total. It's 3.2 or 0.0032 cubic meters per second. So this is how much we're expecting. This is how much we're expecting. Now I'm going to forget that, and I'm going to look at appropriate pipe sizes. Okay, there's a pipe, it's a 200, it has a certain slope. There's a pipe, it's a 200, it has a certain slope. Based on this size and slope, I can calculate Q, I can calculate V for pipe full. I'm assuming the pipe's full. So this is calculated Q, this is calculated V, and then I can look at the actual velocity. We'll talk about that last. Okay, so now I need to pick an appropriate pipe size and slope combination that gives me a Q here that's bigger than here. Right? The pipe capacity, the Q for the pipe, has to be greater than the Q that the population has generated. Right? So this is the next part of the design. Pick an appropriate size slope combination that will give you a pipe size and slope that has a Q capacity bigger than expected flow and a velocity that meets minimum requirements. Okay? So to calculate this and this, you're going to use Manning's equation. Are you all familiar with Manning's equation? Anybody want to give me a sign? Yeah, okay. I'm just going to write down some of the formulas. Okay, so I'm going to do this very quickly. We're going to do one calculation in detail later when we do storm, but let me show you some hand calculations just so you're familiar. So when it comes to Manning's equation, we talk about the velocity. We want to calculate V is equal to R to the exponent 2/3 times the slope to the half, which is square root. And when we divide or take 1 over, we divide by n, the roughness coefficient. Okay, that's Manning's equation for velocity. R is the hydraulic radius. R is the hydraulic radius, which is the area divided by the wetted perimeter. Okay, I don't know if you learned that exactly. Sometimes it's just given to you for a circle. This is a circular pipe, but you can use it for any cross section. What do they mean by that? They want to know the area of the circle. That's A, and they want to know the wetted perimeter. Well, if the pipe is full, the entire perimeter or circumference of the pipe is wet. So this is simply the area, right? R is equal to the area, pi r squared, divided by the perimeter, 2 pi r. And if you cross multiply and cancel, the pi's go away, one of the r's goes away, and you have r over 2. And if you want that as an expression of the diameter, it's d over 4. So the hydraulic radius is d over 4, diameter divided by 4. Okay? So that's really what I would use in the formula. We'll get to that in a moment. S is the slope. And the units for this has to be meters per meter, not percent grade. Okay, you can't use percent grade. You have to divide by 1,000. And then N is the roughness coefficient. Roughness coefficient, which for PVC pipe and concrete pipe is the same, 0.013. Okay, it's just a coefficient of friction on the inside of the pipe. Does this all sound familiar, I hope? Okay. Any questions so far? So in this formula here where it says R, I'm going to substitute D over 4. D over 4 is R, diameter divided by 4. Okay, so let me do that, and I'll derive this formula for you so you know exactly what you want to program into the spreadsheet. So the velocity is equal to D, diameter, divided by 4. Oh, and the diameter has to be in meters. D in meters, right? The diameter has to be in meters, right? So if you have a 300 millimeter pipe, you have to use 0.3 meters. It has to be in meters. So we take D over 4, D in meters, to the exponent 2/3 times the slope to the half, divided by n. Okay, so that's the formula for velocity if you have a circular pipe. Okay, and then Q is simply V times the cross-sectional area, and the cross-sectional area is going to be the area of a circle, right? So pi r squared, right? So Q is equal to V. Once you calculate V, you can multiply by pi, and instead of r squared, you can take D over 2, the diameter divided by 2 squared, which is just the radius. Okay, so on the spreadsheet, we're going to put the diameter of the pipe and the slope of the pipe. And then this is always the same, so it's just a constant, right? The roughness coefficient. And then we can program Q to be this answer times the end area of the pipe, which is the circular area. So that's how we calculate Q and P. Q and V, or V and Q first. So if we go to my spreadsheet, you'll see this calculation. So first I calculate the velocity, and you'll see here's the pipe diameter. Now notice I'm typing in the size in millimeters. Okay, so I have to convert that to meters. So if you go to the velocity, you'll see this divide by 1,000 here, right? So this is the diameter divided by 1,000 divided by 4, right? So that's, and then I raise it to the power of 2/3. So that's the part of the equation that looks like this. That's this part of the equation, right? Which is really this piece, right? The diameter divided by 1,000, because it's in millimeters, diameter divided by 1,000 divided by 4, all of that raised to the exponents 2/3. And then I multiply by the slope square root, or slope to the minus a half. So let's look at that. So then you can see here, this is the slope. I divide by 100. Why? Because on the sheet, I'm typing it in as a percent grade. So this is millimeters. I have to convert it to meters. This is percent grade. I have to convert it to meters per meter, divide by 100. And that's why there's a divide by 100 here. Okay, and then I raise it to the power of a half, which is the same as square root. And then I take the whole thing on top and I divide by n, which is always 0.013. And that's how I calculate the velocity. Once I have the velocity, I have these values for the pipe, I can then find Q by taking the same value, this answer, which is just the same formula here, but I multiply by pi, diameter divided by 2 squared, and that's the part of the formula that's the area of the circle. Okay? And again, the area is the pipe size in millimeters divided by 1,000, so that this is in meters, right? Divide by 2, so that I have the radius, right? I square it, and then I multiply by pi. This is how you type in pi in the computer. Watch, I'll show you here. Equals pi bracket bracket, and that'll give you the value 3.14, as many decimals places as you like. So that's actually pi. Okay, so that's the code for pi. Pi bracket bracket. Okay, so a little bit of calculation. So now, the nice thing is, I don't need to look at this table all the time. This table, where is it? I don't need to look at this table all the time, right? So let's look at that pipe. Let's go to my spreadsheet. A 200 millimeter pipe with a 1% slope should have a Q of 33 liters per second, or 0.033 cubic meters per second, with a velocity of 104. That's the full velocity. Okay, so look at a 200 at 1%. So let's go back to this. Let's look at a 200 pipe at 1%. A 200 pipe at 1% is right here. Right here. Okay, so that's a 200. There's the first number is Q, the second number is V. Now notice this velocity, this is in liters, right? So you have to either multiply the spreadsheet by 1,000 or divide this by 1,000. So it's 34 and 105. If you go to the spreadsheet, you'll notice it's 33 and 104. It's almost the same. And the difference is, when I'm designing, I use the nominal pipe size, a 200 pipe. When you go to the store to buy a 200 millimeter pipe, it's actually an 8-inch pipe, which converts to something a little bit bigger than 200, right? So if you go to that sheet you were just looking at, it gives you the actual pipe size. The actual pipe size, if you look at the top, is 203. So an 8-inch pipe is 203 millimeters, but then we do a soft conversion to metric. It's a 200 millimeter pipe. Okay, so you can see the actual pipe sizes are all a little bit bigger than the metric equivalent, the nominal size. So on the spreadsheet, we generally use the nominal size. And the good thing about that is it builds in a little factor of safety, because the actual pipe is bigger than the nominal size. So if I use these sizes up here, the actual pipe is a little bit bigger, right? So the Q and the V that I'm using are a little bit conservative. If you want to check these numbers, you can type in the actual pipe size, 203. Watch this. So if I type in here 203, you should get 34 and 105. 34 and 105, okay? But we're not going to use the actual size, we're going to use the nominal size. So back to the spreadsheet and make sure it's a 200. Okay, and you can check the same for the slope and size combination, right? It's always what we call a parametric solution. You need both the size and the slope to calculate the Q, the capacity, and the velocity. Okay, so now the nice thing is you can pick any pipe size you want, 300 at 5%, and calculate Q and V for you every time. And that's the beauty of using a spreadsheet. Now these numbers come from the drawing, right? This design is complete. I can't change the size and the slope, so I'm just typing that in. So if I go back to the drawing, right, the size and slope of these are already predetermined, right? It's a 200 at 1%, and this is a 200 at 0.5%. Okay, so that's fixed. I don't have control over that anymore. This pipe is designed, it's constructed, it's being used right now, so I can't change the size. Okay, but I do have to type it in here to show. Now, what are we looking at? And this is the one thing that they don't show on the spreadsheet, but I like to calculate it. I'm going to look at the percent full. So I'm going to look at equals the actual flow, that's the expected flow, divided by the pipe capacity. Right? How much flow is actually coming and how much can the pipe actually take? And this will be a percent full. Right? And if you convert this to percent full, you'll see it's only 4% full. So that pipe has a lot of room. There's a lot of room. And the reason for it is when you're at the dead end of the system, when you're up at the top end of the system, the population is so small that the flow you're calculating is relatively small. But the minimum pipe size has a lot of capacity. So it takes a long time, a big population, a big flow to start to require a bigger pipe size just because of the minimum pipe size, right? If you want to look at the minimum pipe size, I can actually make this a 100, which is not allowed. I can make this a 50, which is a 2-inch pipe, 50 millimeters. Oh, that's too small. How about a 3-inch pipe, 75? That'll work. But that's not allowed. The minimum pipe size is 200, right? So it's only going to be 4% full. And you can check that for all your pipes. Copy, paste. Now it's 14% full. So it takes a long time before this starts to get anywhere near 100%, right? So when you're looking at the pipe system, right, when you're looking at this system, the accumulated flow really won't change the pipe size for a while. So if you look at these, they're almost all 200s. See, 200, oh, this one's a 300. Why is that a 300? Because it's getting a lot of flow from the north. There's a whole area up here. Now it's starting to become significant. And the pipe on this road, which is where the entire subdivision is draining, this pipe is probably the biggest. And you'll see here it's a 300. Not much bigger, right? Because a 200 could take a lot of flow, okay? Because of the minimum pipe size capacity. So we still need to demonstrate this. And if you look at our site, you remember our site? We're taking this entire area and we're putting it into this pipe. Okay? We're putting it into, imagine, the minimum pipe size. So what size are all your pipes going to be in here? What size do you think those pipes are going to be? If this pipe here at the exit is a minimum pipe size. Yeah, you don't even need to do you don't have to go through the calculations to come to the conclusion that all the pipes inside our subdivision are going to be 200. Because the entire site is draining through a 200, so all the individual pipes inside the subdivision are also going to be minimum size. There is one exception, but that's generally true. So really, do you need to do a storm calculation sheet? Yes, it's required, but from a practical perspective, it doesn't matter what you do on the spreadsheet, they're all going to be minimum size pipe because the last pipe you're flowing into is already big enough to handle the whole subdivision. Right? So everything inside is going to be minimum as well. There is one exception to that. We'll talk about it in a moment. So theoretically, if you wanted to, you can actually design your sewer system based on drafting it, what I taught you in CDA. You can draw your solution without knowing what the actual flows are. Because no matter what those flows are, the minimum size of 200 is what you have to use throughout. Okay? Any questions about that? We do need to produce the information. We do have to do the spreadsheet, but it really doesn't matter. It's not going to change the sizes of the pipes. Storm different. Storm is going to be different, right? But the flows are so small at this end of the system, the top end where the dead ends are, that it's insignificant. It's not going to make a change. Okay, any questions so far? All right, now the one thing we are changing is, you remember this total area? It's all supposed to flow through this pipe. There's a piece of the subdivision, a very small piece here, that's actually going to flow the other way based on our profile high point. Remember that? Let me go back to my drawing. I have an area here, an area here, this piece, that's actually going to flow the wrong way, right? So the total area coming out of this pipe, this existing pipe, is actually a little bit smaller. Okay. And this area, although there's no houses connected to it, is going to contribute infiltration to this pipe and this pipe. Okay. So I need to check If I increase the area going through these two pipes, are these two pipes going to be negatively impacted? Do these pipes have capacity to take a little more infiltration area? And that's something you need to check. Okay? So the infiltration area is an additional 0.02 hectares. So on the spreadsheet, what does that mean? Well, let's look at the design. On the spreadsheet, what does that mean? Well, the area now for the first pipe, instead of 0.64 should be 0.66. Okay, which will increase the population, maybe, maybe not. We'll have to do the math and see if it has a negative impact on the pipe. So the expected flow is actually going to go up because we have more area and maybe more population based on that area. But we're going to check the new expected flow against the pipe capacity. Okay, let's take a look at that. So the expected flow, let me go to my spreadsheet. Oops, right? I want to do this. I want to change this from 0.64. I want to add to this 0.02, more area, and see what happens. Okay, you should, or you might, see these numbers go up. And pay attention to this last column here, right here. See if this 14 and 32 go up, okay, by adding area to this. Plus 0.02. When I hit enter, pay attention on the right-hand side here. See if that 14 or 32 changes. Not really. Okay, now, in the other decimal places, past those that you see, there's a change. Let's take a look. So if I leave this as 0.64 and I, and I increase the size of this column, okay, let's just take a look here. If I change the decimal place accuracy here, right, let's look at a lot more decimal places. If I change this plus 0.02, these numbers should change. Okay? The numbers do change. Okay? Not by much though. That additional area doesn't really do much to this. And from a practical sense, if you're only looking at 4 decimal places, which is cubic meters, and if you multiply that by 1,000, it's liters, right? So it's 14 liters. Let me just add 1 extra decimal place, see if there's a difference. Whoops, the other way. Right, so it's 141 and 322. Let's get rid of this and see if it makes a difference. Right, so this is actually rounding up to 14, and this is rounding up to 32. And when I add a little extra area here, 0.02, whoops, plus 0.02, plus 0.02, you'll see those numbers change a little bit, but they all round to the same thing, 0.0014, 0.0032. So there is an impact, but it's so small that it doesn't really change the expected flow. And the other thing to look at is this. Let's look at the percent full. Remember this number here. Let's change this by a few decimal places. Okay, if I get rid of this, and let me just split my screen, view, split screen, okay, so that I can look at what's happening on both sides and zoom in a little bit. So what's happening here, I'll get rid of this. So if I change this, what happens to these numbers? Okay, and I'm going to put this back to 4 decimal places, right? So rounding to 4 decimal places doesn't change anything, okay? Let's look at the percent full. So if this goes back to 64, delete, the percent goes from 115 and 13.7. If I add to this 0.02, it goes to 4.3 and 13.8. So it's very, very insignificant. Okay? And I'm going to say something that's a little crude. I'm going to apologize in advance. That additional area, this little piece here, contributing to these 2 areas here and here, is so insignificant. And the phrase I use, and it's a bit crude, I apologize, it's like peeing in the ocean. It has little to no effect. Yes, you have to account for it, but on a practical level, it does nothing to the actual flows you're expecting on a practical level. Therefore, these pipes that are already in the ground can take that additional area. It's not that big a deal. But from a design and an approvals perspective, you have to show that analysis. You have to show that you've considered the fact that you're changing the drainage pattern a little bit. Now I'm showing you this here, and like I said, it's very insignificant because this procedure has to be done for the storm sewer as well. When it comes to the storm sewer, we're actually taking a lot more area out of the site and going a different way than we are with the sanitary. So I want to discuss it here because it's very simple, but the process has to be followed as well for storm, and those areas going to Chuchmak are much, much bigger than just this sanitary area. Okay, so you have to do the equivalent analysis, and in that case, it's a significant increase. So we really do need to check to make sure that those pipes, those storm pipes are big enough to handle the additional flow we're assuming to take to the north. Okay, so part of the assignment is to analyze the sewers on Chuchmak for sanitary and storm, and make sure that the additional flow or the increase in expected flow doesn't surpass the capacity of the pipes that are already designed and built. You can't change the size and the slope. So if you need to increase the slope to get capacity, or if you need to increase the size of the pipe to get capacity, it's not going to work because the pipes are already built. You don't have control over size and slope anymore. Inside the subdivision, yeah, you can do whatever you want because you're proposing the pipes. But once they're built, you can analyze them for capacity, but you can't change them because they're already in the ground. So that's part of the analysis that has to happen. Any questions about this? So on the spreadsheet that you're going to hand in to me, I see this analysis. I want you to calculate the additional flow. So change this from 64 to 02 and show this calculation. Now, I'm asking you to do this for two reasons. One, it's something you should do when you're doing a design. So you have to show the change and what impact it has. And two, it gives you an opportunity to program the spreadsheet so that now you can copy and paste formulas into the actual proposed subdivision to design your pipes. And the nice thing is if you do this one first, because you're calculating things that you have solutions for from the PDF, you can check your formula programming, right? So if you're getting the same numbers that are on this PDF on your Excel sheet, you know that the programming or the formulas you're using are correct, right? Once you've programmed these two lines, then you can cut and paste the formulas into other cells for everything you have to do inside the subdivision, right? So all these pipes have to be proposed. Okay, and there are, according to the maintenance holes, there are at least this many pipes, right, including the existing. You want to check the last pipe. Okay, so this is the system you're designing. Okay, so you have 1, 2, 3, 4, 5, 6, 7. You should have maybe 8 pipes proposed, and then I want you to actually show the first existing sewer to show that that pipe that's already in the ground has the capacity to take what we're proposing inside. Okay, so you have to show this on your spreadsheet. Okay, now the numbering system for this, I'm going to show you. This is how I would number it. What they're doing in this subdivision is backwards to what I taught you in CDA. Okay, I want you to do what I taught you in CDA. I want you to start at the bottom at the outlet and work your way upstream by increasing the maintenance hole numbers. So I'm just going to draw this here off to the side so I can discuss it. Let me just get the sketch ready. One here, and then there's the existing pipe. Sorry, I'm just redrawing it so I can discuss it. Okay, so let's look at my hand sketch. Okay, so there's the sewer system. So this existing maintenance hole, according to the drawing, is maintenance hole 60A. That's this one, 60A. All right, so this is 60A for the sanitary. This one here, if we're moving it, right, and I am moving mine, you can see on the drawing, right, it used to be over here, but I'm putting it over here. I'm going to use the same number so that I have an existing number and an existing number that's describing this pipe, albeit it's going to be a little bit short. So 301A. Okay, so this one is 301A, this one. Even though it's a proposed new location, I'm going to use the same number, 301A. Okay, so those two are fixed. So if you move that one, just keep the same name. This is existing on the road. This one's going to be moved perhaps. And now you have to number your own. Now start at the bottom and work your way up. Okay, so the next one, this is manhole 1A. When you get to this junction, this is manhole 2A. And then from there, you always go the shortest distance first, right? Or the smallest number of manholes first. So I've got 1, 2 here. I've got 1, 2, 3, 4 here. I'm going to go up this short piece first. So this is 2. This is going to be 3A. This is going to be 4A. 4A. And then I go back and continue. 5A, 6A, 7A, and 8A. Okay? So to describe this pipe from 8A to 7A, describe this pipe from 7A to 6A, and so on. So when you look at the numbers on the table, when you go to the spreadsheet, I've got a high number flowing into a low number, a high invert flowing into a low invert. They've done it backwards in this subdivision. If you go to Chuchmak, let me show you the drainage area, they've done the opposite of what I just said. So if you go to here, you'll see the numbers are getting bigger as you go downstream. 56A flows into 57, 57 flows into 58, 58, it's going down this way, flows into 60, 60 flows into a higher number. Well, flows into 59, okay? So the numbering system's all a little bit wacky. Go with what I taught you in CDA. Start at the bottom and work your way upstream by increasing the maintenance hole numbers. So this is the system I expect you to use, right? Take the first two, leave the names. The first proposed maintenance hole is 1, go to the junction 2, and then go the least number of maintenance holes first. So 3, 4, and then go back and continue, 5, 6, 7, 8. And they're all flowing out, right? They're all flowing this way. And eventually out, right? I just need to check that this pipe still has the capacity for this area. And I'm not worried about it for a couple of reasons. One, I went from commercial to residential, so I'm expecting lower flows because of that. And I know that this pipe was sized for commercial, and now I'm going residential. So the expected flow in this pipe should actually be proposed less than it was before. Okay? And if you want to check that, you can actually go to the drawing. Remember the drawing here? It says 3.49 hectares at 90 people is 315. So that's the total population that this pipe was designed for. If you look at your drainage, areas, just check my drainage areas. If you look at your drainage area information, if you add up all these populations, don't include this one because it's going a different way, right? If you add up all the populations from these, they should all be a little bit less than 315. Less people, less flow. And if you want to check the math, you can, right? 33 plus 40 plus 22 plus 15 plus 30. These are my areas, right? You're going to have slightly different populations depending on how you drew your drainage areas. If you add up the total population here, you should get something less than 315. Okay, why? Because I'm using 135. I'm using 135 for the townhouses, but I'm using 55, less than 90, for most of the subdivision. Right, so I'm expecting a much smaller total population for residential than I am for this commercial property. So you'll see that when you do the calculation, right? You can compare your population to this 315 for the total and notice that it's significantly smaller. Okay, or you can do the math now if you want, right? You can go through the calculation, just add up your total populations for all these bubbles and see that it compares to 315. It should be a lot less than 315. So intuitively, you can kind of estimate, what the difference is, but you really want to compare flows. What's the flow right now in this pipe expected, and what's the flow expected after we change this to residential? Okay. So if we go to the spreadsheet, you'll actually see this calculation. So if we go back to the PDF, let me zoom extents. So if we go to, I believe it's on which page now, the 4th, I think. It's on, just looking for that maintenance, so that 301. 301, 301, where is it? 301, oh, here. Here we go. Is it here? No, not here. No. Is it either? Where is it? Let me find it, sorry. Not here. Oh, here it is. It's on the same page. My mistake. It's on the same page. So if you look on the fourth page of 5, right here, you'll see the commercial property, which is right here. Contribution from commercial block, not in subdivision. That's the actual piece that we're designing, manhole 301A, right? So if you go to the drawing, if you go back to the drawing, we're looking at manhole 301A, right? So from here to here, 301A to 60A is on the spreadsheet, right? 301A to 60 is contributing. There's the 349, and then they calculate the population to be 315. And if you continue to look on this, you'll see the expected flow is 5.1 liters per second. We're going to calculate, and I'm pretty sure ours is going to be less. So this existing pipe, the 200.5% that's in the ground, should have the capacity to take whatever we do, because I'm predicting we're going to do a lot less than this. Okay, so that's something you can double check. So I'm kind of giving you a target, right? When you do all the math inside the subdivision on the spreadsheet, right? So on this spreadsheet, when you do all the math for the pipes inside the subdivision, right, for all these pipes, the flow you're going to calculate in this pipe better be, or should be, less than 0.0051. And if it's not, then you should double check your calculations. Something's wrong, okay? Because I'm predicting a lower population with a lower expected flow. So I'm just giving you a sense of the range, right? I don't think it's going to be that high, but certainly it has to be less. All right, so just keep that in mind. So I'm just analyzing what the expectation is. So I don't know what that number is, but I know it's going to be less than 5.1. Okay, does everybody agree with that statement? Does that make sense? All right, we're proposing a much lower population, so we expect a lower flow. Okay. Now the minimum pipe size, as discussed in the standard, right, is shown as a 0.5% pipe with a minimum slope. Sorry, a 200 millimeter pipe with a 0.5% slope. So that's in the Halton standards. So if you read this document, you should see that information for pipe design. Here's Manning's equations again. It's actually, and the interesting thing is that Manning's equation for flow is the same for sand and storm, right? The circular pipe doesn't care whether it's rainwater or sanitary flow, right? Its capacity is calculated the exact same way. So the discussion we already had for Manning's equation is the same for sand and storm. So what we're looking for here, for residential areas, right here, for residential areas, the minimum pipe size shall be a 200 millimeter pipe. Okay. How a 150 millimeter pipe can be used for the first upstream section of a sewer. That means the dead end pipe can be a little bit smaller, okay? And if you know the characteristic behavior of this formula, right, there's two things, right? There's a size and a slope. There's a size and a slope. Let's have this discussion if you haven't before. Based on size and slope, how does the change in size influence the capacity? So if we look at the size, so the diameter of the pipe and the slope of the pipe, right? We have the two parameters to calculate Q and V, right? If I make the pipe size bigger, if I increase the pipe size, what happens to the capacity? Does it go up or down? A bigger pipe has more capacity or less capacity? Does this go up or down? It goes up. So the bigger the diameter, the bigger the capacity. The smaller the diameter, the smaller the capacity. Okay? When it comes to slope, what happens if I increase the slope? What happens to the capacity? Does it go up or down? If the pipe is steeper, if I make the pipe steeper, does it have a bigger or a smaller capacity? Talking about Q. it goes up. The steeper the pipe, the more capacity. So the opposite is true. If the pipe gets flatter, then the capacity goes down. Okay? The velocity is a little bit different. The velocity is a little bit different. If the pipe size gets bigger, what happens to the velocity? If I increase Q, if the diameter goes up, what happens to the velocity? Does it go up or down? It goes down. It has the opposite effect. Okay, and you can see that on my spreadsheet. Watch. If I zoom in here, just as a calculation example, let's go to the end where the pipes are, right? Watch Q. If I increase the pipe size, if I go from a 2 to a 300, this 33 gets bigger. If I make it bigger, 450, it gets bigger. So the bigger the size, the bigger the capacity, right? So if you make the pipe bigger, it has more capacity. The slope is different, right? The slope it has the same effect. If I make it steeper, Q goes up as well, right? So if it's 1%, it's 33. If it's 2%, it's 46. If it's 3%, it's 57, and so on, okay? So if you increase size and slope, capacity goes up. Velocity is a little bit different. If the pipe gets bigger, watch what happens to the velocity. It actually goes up a little bit, okay? If the pipe gets bigger, the velocity goes up. What if the slope what happens if the slope changes? What happens if the slope changes? If the slope changes, if I make this bigger, the velocity goes up. Sorry, that's backwards. Hang on. Make sure I'm calculating this right. 200 goes to a 300. The velocity goes. Sorry, let me double check that. It's supposed to go down. Maybe you see, now I'm questioning my own calculation. Velocity full. So Q, if this gets bigger, velocity goes up. If Q gets bigger. Okay, so the actual, I'm looking at the actual, sorry. So 200. The actual velocity goes down. So if the pipe gets bigger, the actual velocity goes down. If the pipe gets bigger, the actual velocity goes down. So it depends, there's a sweet spot, right, of where it gets bigger or smaller, depending on how full it is. So if I want a greater velocity, I want a smaller pipe, right? The actual velocity goes up based on the percent full, right? If the pipe gets smaller, remember it said the minimum size is a 200. If I use a 150, if I make it a little bit smaller, the actual velocity is going to go up. If I make it a little bit smaller, the actual velocity goes up. So that's what we're trying to do. So the first pipe, unless it's full, obviously, the first pipe, even though the minimum size is a 200, right, we're going to allow the top end of the system to be a 150 to try and get a little more actual velocity. Okay? And that's why it's right here. It says in the standard, a 150 pipe can be used for the first upstream leg of sewer. And that's an attempt, because the pipe's not full, to get the minimum velocity. And there is a minimum velocity requirement. Let's look here. I think it's written down. Minimum velocity is right here, 0.6 meters per second. Right? The actual flow can't be less than 0.6. Well, look at the spreadsheet. It's very difficult to do. If you look at the actual velocity, especially at the dead end of the system, right? This Chuchmak pipe, these two, this is the dead end of a system, right? The two top pipes. If you look at the actual velocity, I've got 4.9 and 5.2. Much less than the standard. Much less than the standard, which is 0.6. Okay? And it's very, very difficult to achieve. The only way to get a higher velocity is to make the pipe smaller or steeper. So let's try that. I can't change this, right? So if I was to use a 150, this actual should go up. That's good. And as a steeper pipe, 2%, the actual should go up. If I make it steeper, the actual should go up, and so on. So that's part of the game that you have to play. Try and get this up over 60. Now, it's almost impossible at the last pipe. So to get a little bit of extra flow, right, the minimum is 200. Whoops, 200. And the slope we used was 100. Sorry, 1. At the dead end of the system, again, if we look at the drawing, right, there's no more pipes. This pipe here could have been a 150, right? There's nothing else connected to it, right? This is the dead end. Instead of using 200, I could have used a 150. I could have used a 150 and try and get this actual flow up a little bit. And the reason for the minimum flow is so that you keep the flow going, and really what it's concerned with is the solids suspended in the water, right? So when you flush your toilet or water goes down the drain or the sink in your house, there's always bits of solids mixed in. And if the if the flow is too slow, those solids start to percolate out and stick to the bottom of the pipe. So that 0.6 minimum, that's the reason for it, the 0.6 minimum is what they call scouring velocity. If the water is moving at least 0.6 meters per second, then you can expect that the suspended solids in the flow will remain suspended. They'll move with the flow. Anything less than 0.6, now you have the percolation of solids, kind of settling to the bottom and then kind of sticking to the bottom of the pipe. And over time, it could clog the pipe or compromise the cross section, compromising the capacity. Right? Now, all this means, if you can't do it, right, if you look at this flow, you can't make the pipe 5%. You can't make the pipe 10%. It'll come sticking out of the ground, right? So there's a practical limit. So at some point, you have to accept that I've done my best, and I don't know why they didn't use a 250 here. I would have. You've done your best to get to 0.6, but unfortunately, you just couldn't get there. What that means in a practical sense is this pipe will require more maintenance than other pipes that have the minimum velocity, right? Because you can expect solids to percolate and stick to the bottom of the pipe, okay? So don't worry about the minimum requirement. You should know about it. It could be on the quiz, right? You should know this value and where it comes from, right? Section B4. You should know that that's the minimum velocity, but in practice, it's very difficult to achieve. And you'll see even this design has a lot of substandard pipes. Look at this one, it's only 0.3, 0.36, 0.33. 0.59. If you look at any of these flows, right, a lot of them don't make it up over 0.6, right, 0.48 and so on. And the town recognizes that. So yes, it's a requirement, but very difficult to achieve, especially when you're looking at a very small tributary. Okay, so don't do anything about it, but do your best. Make the pipe, and this is the requirement. I'm going to show you again, and we did this in Richmond Hill as well. If we go back to my hand sketch, whoops. If we go back to my hand sketch of the sewer layout, right, we had 1, 2, 3, 4, 5, 6, 7 short pipe, and then the existing. So if you remember these, right, that was the schematic. These two pipes are at the end. So all the pipe sizes are going to be 200 at 0.5%. Sound familiar from CDA? Except for this pipe and this pipe, the last two pipes. This pipe is going to be a 150 at 1%, a little bit smaller, increase the velocity, a little bit steeper, increase the velocity, and this one is also going to be a 150 at 1%. So these two are the exception. All the other pipes are going to be 200 at half. For the same reason that we did it in Richmond Hill, it's a requirement in Milton. So I would do that to try and get the scouring velocity at the smallest flow to bump up a little bit, so that we don't have any of that settling issue. Okay, so everybody clear with that? So when you create your spreadsheet, the pipe sizes are all 200 at 0.5%, except these two. Calculate your flows based on that, right? And at the end of the day, no matter what you put on the spreadsheet, this is the design. It's just a matter of detailing the flow in each pipe. You have to show that. It's not going to make a difference to your pipe size and slope. Any questions about that? Okay, so the sanitary system compared to the storm is a lot less tricky, a little more straightforward in terms of what you have to do. Okay, so on your spreadsheet, I want to see Chuchmak. I want you to analyze the two sewers on Chuchmak Crescent, and then I want to see all the pipes inside the subdivision, including the last pipe or the first existing pipe, which is this one. So make sure you include this pipe on your spreadsheet. After that, doesn't matter. I'm not going to worry about the rest because I know they're not going to be negatively impacted. If the flow coming out here is going to be less, then this pipe that it's flowing into and this pipe that it's flowing into is accepting a little less flow. They're not going to be negatively impacted. I'm actually going to decrease the flow. So I don't need to worry about those pipes. Right? I just want to show that this one is going to have less than before, therefore the whole system has less than before. Okay? But these two have a little bit more, but you saw how insignificant it is. Right? And I guess by the same token, this will have a little bit more, but it's very insignificant. If you want to add this to the sheet, you can, but I'm going to keep it simple. Let's just look at these two local sewers. Okay, so if you wanted to add 58A to 60A, 1/3 pipe, you could. If you do that, it gets a little more tricky. So if we look at this, it gets a little more tricky. If you're looking at 58 to 58 to 60, this pipe here, there's a lot of flow coming from above. So it gets a little more tricky. Okay? If you want to do it, that's great, go ahead, but I'm not going to make that a requirement. Right? So coming from here, right, this pipe here is taking the flow from like the entire subdivision to the north, right? Almost everything up here is coming through this pipe. So if you want to do that analysis, you can, but again, it's going to be very insignificant. If you look at that pipe size, right, that 300 at 0.3%, go back to the spreadsheet, it's a 300, which is 60 to 59, I believe. Let's just double check. Sorry, we want to look at 58 to 60, 58 to 60. 58 to 60 is this line here, is this line here. Look at the population, 2,000 people. And the flow, the expected flow is this, and you're going to increase it by almost nothing, right? So the area, the total accumulated area to this point here, the total accumulated area is 29.86 hectares. That's the total area. You're going to increase this from 2986 to 2988 and see what happens. And it's very insignificant. So I'm not worried about that pipe, okay? But I am worried about the two local pipes on Chuchmak. Okay? So if you want to do that one, you can, but I'm not going to make it a requirement. So your spreadsheet at the end of the day for sanitary should include the two sewers on Chuchmak with the revised area. Make sure you add that area, right? This area here, whatever it is, might be bigger or smaller depending on your design. Add that area to this and see what happens. Yeah, and you'll see it's next to nothing. Okay, so analyze Chuchmak and then design all the pipes, including the first existing 301 to 60A. And that's what's required. So I want you to hand in the spreadsheet and I want to see calculations. Okay, so you can see here, the things in gray are typed in, everything else is calculated. So these are the columns where you type information in. The other columns, the blank ones without color, should be calculated. Okay, maybe with the exception of the population. If you want to change the population by hand, you can. Okay, so please take the time to explore the functionality of the spreadsheet to ensure that you know you're programming it correctly. Okay, any questions? So let's look at the sanitary database again. Let's talk about Civil 3D a little bit and the design approach for this particular subdivision. So we are connecting to LedgerWay. Let's look at the LedgerWay profile. So if we go back to LedgerWay plan and profile. So we're connecting to this sanitary sewer right here, right? 301 to 60A. This is the pipe we're connecting to. If you look at the sewer on LedgerWay for sanitary, you'll see here's the design of the road. Here's the water main, right? With the minimum cover 1.7. We'll deal with that last. And then we can see the sewer, the storm sewer is pretty much flowing in the same direction as the road. The sanitary is doing the opposite. Look how deep the sanitary is. This is the sanitary sewer here. Right? You can see a maintenance hole here. You can see a maintenance hole here. The sanitary sewer is actually flowing out of the subdivision this way and out, and then connecting to this main sewer on Louis Saint Laurent. Look how deep it is. Right? There's the sewer on the road to the south. Here's our proposed sewer out of the subdivision, and here's the sewer, the sanitary sewer on Ledger Way. You can see how deep it is relative to the road. So we know it's deep enough from a geometry perspective to take these sewers. Okay, I'm not worried about that. So we're going to take a slightly kind of opposite approach to what we did in Civil 3D last semester. Remember CDA? Let's go through that one more time. So in CDA, if you remember, we had an existing road. We had an existing road, and we were connecting to it with our cul-de-sac and elbow. Remember this? Right? And that was our proposed road. And we had two maintenance holes. We had a sanitary and we had a storm, right? Existing. And then we designed our sewers, right? We came in, we did a little jog here, and we went all the way to the end here. And we did the same with sanitary. Right? So everybody remembers that layout from last semester. The design then started with these inverts. I know the invert here, I know the invert here, and then I went upstream, right? So I went distance slope, add the minimum drop, distance slope, add the minimum drop, distance slope, add the minimum drop, distance slope, get the invert. So that's how we calculated this. So in the profile, the road was going uphill and the sewers were doing the same, going up and then jump up a little bit, then jump up a little bit, and then jump up a little bit, and so on. The sewers were basically parallel to the road. Same with sanitary. Storm. Storm was doing the same thing. Right? We basically went uphill. Remember this? Okay. So we started at the bottom and we worked our way up. For the sanitary, and only the sanitary, we're going to work backwards. We're going to start at the top and work our way down. That way, if I start at the top with minimum cover, and we'll discuss what that is in a moment. If I start at the top and come downhill, remember the slope of the road is minimum, except for the elbows. If I start here and I come down, then I will calculate an invert that's a lot higher than the existing sewer on Ledger Way. That way, if I start at the top with minimum cover and come down, instead of starting at the bottom and coming up, I won't be as deep as this sewer will allow, right? So this is way down there. I don't want to be that low in the subdivision. In the subdivision, I just want to be with a minimum cover. The minimum cover requirement is in the document. So there is a minimum cover requirement in the Halton standards. We can look it up here. It'll tell you this, the pipe requirements. Should tell you, sorry, here. Let me just find it under pipes. Pipe depth, right here. Note the section. The top of the wastewater main, this is what I'm reading here. The top of the wastewater main shall be a minimum of 2.75 meters below the center line elevation of the road, and not less than 1.4 from the ground surface to any other location. Okay, so the minimum is 275. So if I know the slope, if I know the elevation on the road, I could subtract 2.5 and then subtract the pipe size. And that'll give me the invert at the top end of the system. Right, so let's go back to the sketch, right? Not this sketch, but let's talk about this here. I'm going to draw those pipes again. Right, I'm going to go from here to here to here. Same thing down here. Oops, that should be the same location. And then we have the existing, a proposed short pipe and then an existing. Right? So what we're going to do is we're going to start at the top. Remember, these are all flowing this way, right? Coming out to here. So I'm going to find out what the elevation here is, right? And I know the road. I'm going to find out the elevation of the road. I'm down 2.75. That's the top of the pipe. Then I'm going to subtract the size of the pipe. And that'll give me the invert of this pipe. And then I'm going to go down at 1% for this pipe, whatever this distance is, to get this invert. The start, the end. Subtract the drop. Go downhill. negative 0.5% over this distance. Subtract the drop. Slope distance, subtract the drop. Slope distance, subtract the drop. Okay, now when you get to the junction, you have to think about that. Once you get to the junction stop, you'll have an invert here. Here then, again, you'll take the road elevation, go down 275, and go down the pipe size. That'll give you the invert to start with here. I put the X here, I really mean the center of the structure, right? Then you go down 1% to get this invert. You subtract the minimum drop to get this invert. You go down 0.5% to get this invert. Whichever one of these is lower is what you're going to use to calculate this one. Whichever one is lower, right? So take the minimum drop, you're going to get a number here. And then from here to here, take the minimum drop, and you're going to get a different number. Whichever one is lower is the one you use going forward. Okay, so you're going to get a number for an invert here, you're going to get an invert here. You're going to take that, subtract the minimum drop, get a value. You're going to take this invert, subtract the minimum drop, get a number. And the minimum drop, again, is going to be based on exactly what I taught you last semester. The difference in pipe size between the up and downstream, the difference in pipe size between the up and the downstream, and the angle. Is it straight through? Is it 45 degrees? Is it 90 degrees? There's always two options for the minimum drop. Difference in pipe size, minimum drop based on direction change. Okay, we'll look at those in a moment. And then you continue your way down. When you get to the end, when you get to here, you'll find you're a lot higher than the existing invert. And then this system is no deeper than it needs to be. Okay, so a little bit backwards. Last semester we started at the bottom, a minimum slope up, minimum drop up. And we piggybacked our way upstream, we came up. This year we're going to start at the top for sanitary and work our way down. Backwards. Okay, so you're going downhill and you're going down the slope, you're subtracting the drop instead of adding the drop and going up to the pipe and so on. You're still going to digitize in the direction of flow. This is the start, this is the end. This is the start, this is the end. This is the start, this is the end. Each pipe has a high invert, that's the start, and a low invert, that's the end. So that doesn't change, right? But we're just doing the math downhill instead of uphill. And that's so that we don't get unnecessary depth on the sanitary sewer. We start with the minimum cover and then we go downhill. If we go down at 0.5%, just like the roads, they'll be parallel and we'll always have approximately 275 of cover, 75 meters of cover. Okay, so that's how you design the sanitary. And again, I would suggest doing what I taught you last semester. Calculate, get that elevation. Where do you think the elevation comes from of the top of the maintenance hole? How are you going to get that number? What's the elevation here of the maintenance hole? Where do you think you're going to find that? What would you do to, if I asked you for the top elevation of that maintenance hole, how would you get it? Anybody have any ideas? Anybody else? A little more specific than that, Trong. Not the corridor, but the corridor surface. Exactly. Okay, so if you go back to the drawing, right, if I hover here, if I turn my surface on, right, if I make sure it's visible, so if I go to my surface for the roads, if I turn everything on, right, there's my road surface, whoops, there's my road surface, object viewer, there's my road surface, right, that's all my roads. Remember, there's a high point here, there's a high point here, there's a low point here, and then it's all falling out. This is Chuchmak, this is Ledger Way. I can actually hover here and it'll read the surface. And look at where it says roads. That's the corridor elevation. So in this case, the top elevation, approximately, there's a more accurate way of doing this, but approximately is 195.929. I would just work with two decimal places, 195.93. Subtract 275, subtract the pipe size. This is the dead end. I'm going to use a 0.15 or 150 millimeter pipe. Now I have my invert at the top end, and I'm going to go down the pipe, subtract the drop, down the pipe, subtract the drop, and so on. Okay, so it comes from the road corridor surface model. Okay, the road corridor surface model. And that's the source data. There's actually a way of getting that information more accurately. I'll show you that in a moment. Okay, no display. Okay. So what are the minimum drop requirements? Remember in Richmond Hill, we have the same two requirements. There's two options, whichever one is bigger. So let's look at the standards again. If we go back to Halton region, right, we want to look at the minimum drop. Should say something about it here. Okay, now they want you to calculate the drop based on the change in direction. Okay. See, the minimum is 0.03 and 0.06 for almost 45 degrees or almost 90 degrees. The numbers I used that I gave you last semester are actually much more conservative than the values you see here, right? They want you to calculate all this stuff. Did you calculate this? Did you calculate velocity head and head loss through a maintenance hole? Did you do all this last semester? Did you actually calculate the drops? Did you do that with Professor Marizzi last year? Anybody remember doing this for SAN? So there is a calculation. I'm going to ignore the calculation, and I'm just going to use the rule of thumb I gave you last year. Okay. So you'll notice here it's somewhere between 15 millimeters, 30 millimeters for straight through, and then 3 millimeters or 6 millimeters for 90 degrees. Okay. That's a lot less than what I'm going to ask you to do. Right. If you look at mine, I always said this. For a sanitary sewer, if you're going straight through, use 0.03 meters. If you're turning at 45 degrees, and again, it's the deflection angle, 45 degrees, you're going to use 0.06 meters. And if you're turning 90 degrees, right, if the deflection angle is 90 degrees, I want you to use 0.09 meters, right? 369. This is for sanitary. Okay. That's a lot more conservative than the minimums described in the document, right? If we go to Halton, right, it says to use anywhere between 1.5 and 30, right? So between 0.015 to 0.030, and then it asks you to use 0.3 for a 45, 0.03, and then it's asking for 0.06 meters. And look at what I just wrote down. This is the standard on this side, but I want you to use this, which is much more conservative, right? Instead of 15 to 30, use 30. Instead of 3, use 6. Instead of 6, use 9. Okay? So you'll be much higher drops than what the minimum requirements are. Okay? And that saves you the headache and frustration of doing the calculation, right? The velocity head, times 0.25 and so on, right? So you calculate it, and you have to calculate it at every maintenance hole. So it's a bit of a pain. It's easier to use a rule of thumb that's conservative than to take the time to calculate this. The only time these calculations are significant is if you're talking about a large flow with a huge pipe, like a 1200 millimeter pipe or a 2500 millimeter pipe, like the size of pipe you can drive a car through. Then it gets significant, right? But for these smaller local sewers in your typical subdivision, you don't need to worry this too much. Okay, so if you're going to take a quiz or a test, online test on this material, here is the reference to how you calculate it, but that's not what we're going to do. Okay, the exception is we're going to use the rule of thumb I taught you last semester. That's one thing to take into consideration. The other thing is the match obvert. I'm not sure if that's covered here. Yeah, right here. Match the obverts. What does that mean? Right, for every maintenance hole, the pipe coming in flowing this way and the pipe coming out flowing this way. This, and if we all calculate at the center, right? But the top of this pipe has to be the same or higher, can't be lower. So you have to match the obverts, or the upstream pipe obvert has to be higher than the downstream pipe, the same or higher. You can't have a pipe where the top of this is lower than the pipe going out. That hydraulic jump is not allowed. So this is not allowed. You have to be the same. These have to be the same, or the upstream one has to be higher. They have to be the same or higher upstream. Okay, so that's what they mean by match obvert. So if you remember the calculation you did last semester, when you do your minimum drop, you have to take the difference in the pipe size, That's your match obvert condition. So if you know the pipe sizes, take the difference and then compare it to the angle requirement. You'll get two values. Whichever one is higher, that's the one you use, just like last semester. Okay? But remember, we're subtracting the minimum drops, right? We're going downhill. We're going to start here. We're going to go to here. The difference in the pipe size, that's one number. Straight through, that's another number. Whichever one is bigger, that's what you subtract from this invert to get this invert. And then you go downhill, right? 0.5% based on the length. And then you're going to take this invert. You're going to take the difference in the pipe sizes. That's the match obvert condition. And then you're going to take the angle requirement. That's another one. Whichever one is bigger, that's the drop you subtract, and so on. And you work your way downhill that way. Again, when you get to here, whichever one is bigger. So you have an invert here. How do these two relate? What's the minimum drop between here and here? Well, 90 degrees, or the difference in pipe size. What's the difference in drop between here and here? Straight through, difference in pipe size. Then you get a number. You'll have two inverts for this pipe. The lower one is the one that governs. So this might push this down, or this might push this down, whichever one is lower, so that both pipes fall in. No, you don't need to change the location of your maintenance holes. Okay? I think they're pretty good for the layout you have. If it's similar to what I've shown you, okay, it should be good enough to design, right? You should have 1, 2, 3, and maybe a short little pipe here. Existing, don't forget the existing. And then you should have 2 here, a short pipe here, and then 1 more here. So generally you should have 1, 2, 3, 4, 5, 6, 7, 8, plus the first existing pipe, 9 lines on your spreadsheet. So that's a lot of work already. What time is it? 3:20. Okay, we still have about an hour. I think that what you want to do for homework for next week is design your sanitary sewer. I want you to get the spreadsheet ready, including Chuchmak, and draw your sanitary sewer system in the profile, starting at the top and working your way down. Okay, I'll demonstrate that next. And then you could have it drafted, have the calculations done, and before I see you again next week, you have your sanitary system complete. Then next week, I think I don't want to confuse you. We'll deal with the storm sewer. Okay, so I'm going to finish today's discussion with the drafting of the sanitary system. And remember, I can draw it without knowing what the flows are, because the sizes and slopes are not going to change. So it's a little easier to deal with than the storm sewer. Okay, so that'll be the next thing. Okay, I'm going to show you how to draw it in the profile. Okay, any questions so far? Okay, so the next thing will be a review of what we did in CDA for the most part. So Stephen, if you don't have enough, like one common mistake was to make this pipe go from here all the way to here. They made this one pipe. If you don't have a maintenance hole in between this one and this one, you should put one in. It's too far, right? This is longer. If you measure the distance from the center here to the center here, you'll notice it's bigger than 150. So you need at least one maintenance hole here, and for the same reason, you're going to need one here. Okay, so make sure you have at least 2 here and at least 2 here. 1 here and 1 here. Now, some of you may have had a solution where you kinked this pipe like this and didn't do this, so you might have 1 less pipe. Not the desirable solution, in my opinion, but it's acceptable. Okay? But certainly, in general, yours should look like this. So how do you digitize this system, right, to create the database? There is a reference document from CDA, right? It's a 1-page document that shows you how to do this. But I'll demonstrate it here. Again, I'm just going to turn off some of the noise. There's too much information. Hang on a second. Sorry, I don't want to. I'm going to turn it off. Sorry. Whoops, turned off the sanitary. Oh no, the sanitary sewer is there. I'm going to turn, I think I can turn the center line off. Maybe. layer 0. I'm going to turn off layer 0 just temporarily. Oh no, it won't work if I do that. Okay, I'll just use the maintenance holes. Oh, there it is. It did turn off. Okay. So there's the sewers, right? You want to digitize it. It might not work with 0 off because the pipes by default go on layer 0. So I'll turn that back on. Okay. So I want to digitize the pipe. I'm going to turn my O snaps to center. So I'm going to go from center to center, all the circles that I drew. Okay. Always, always, always start at the top and digitize in the direction of flow. Always. Okay. Now this one gets a little more sophisticated because there's a junction here. And what you might want to do is digitize not only this pipe, right, but it'll actually start here, but these two pipes as well. Okay. I'm not going to do it now, but I'll show you why later. Okay. There's something that happens that's specific to the database that you might want to use that for. Okay. So let's look at this. So how do you digitize the system? Okay. So my O snaps are set to center. That's all that's on. And now I'm going to go over to pipe networks. And I'm going to create a new one. Whoops, network, create a new by layout. So I have to give it a name. This is sanitary. Remember, use a 3-letter caps here because that text string that you type there will actually be in the label for the pipe, indicating which system you're working on. The network part list is going to be parts, just like last semester. That's kind of the digital hardware store of where we're getting our parts. The next thing I want to look at is the surface. So this is the corridor, the roads, that establishes the top of the maintenance holes. The alignment name, well, you're going to have to do this twice probably. The alignment name is actually, depends which road you start with. I'm going to start with street B. Okay, I want to start here. Remember, these are the higher values, right? So this is 8, this is 7, this is 6, this is 5, 4, 3, and this is 2, and then so on. So I'm going to start on street B. So I'm going to start with street B. Structural label for the plan view, and the pipe label for the plan view. So you have to change everything you see here, okay? And that's exactly as I taught it to you last semester. You'll do this again with all the same settings, except this will say STM when we do the store. Okay. So I'm going to say OK. You'll get a dialog box. Keep the default size, the 1200 millimeter diameter maintenance holes. So don't change this. But here now we want to start digitizing. And I'm going to use PVC pipe. Okay, so I'm going to go with PVC pipe. And the first pipe is a 150. And now I'm going to start digitizing. So I'm going to start here, click. And don't worry about the panorama. Don't worry about any of those warnings, just keep going. So there's the first structure. The next structure is here. And let's look at the label. It should give me a 150. Yep, there it is, 150. And see how you get the length for free? 87.1. The next pipe, I'm in the middle of the command. I can actually change the size on the fly, make it a 200. So I'm going to snap here. I'm going to snap here. I'm going to snap here. And then I'm going to continue downstream. I'm going to snap here. I'm going to snap here. And I'm going to do one more. I'm going to snap here, the last existing maintenance hole, right? So I can define this pipe. And I'm going to stop, enter. Okay, so I've digitized that part of the system. Now I'm going to go back and start here and work my way down again. So I'm going to start the command. It's this button here. You want to do pipes and structures. So I'm going to start this again. Before I pick this, I'm going to change the pipe size back to a 150. I'm going to go from here to here. There's a 150, and then the next one is a 200. So I'm going to change this on the fly. And now when I snap, I'm not going to snap. Watch the little indicator. Instead of snapping to the center, it recognizes there's a maintenance hole there. And look at the little magnetic pointer. See this? See, it looks like a pair of, see this? This is this one. See the two squares with the lines? It looks like a pair of broken eyeglasses. That's telling me this is a Civil 3D OSNAP. It's going to connect to the structure. So instead of creating another maintenance hole, it knows there's a maintenance hole there. It's going to connect to it. So I don't want to have two maintenance holes on top of each other digitally. I only want one. So when you see that indication, you know it's going to connect this one. You know it's going to connect to the structure. Okay. So make sure you connect to the structure. This piece here. Okay, so when I snap here, it should only have one. It didn't create another structure. Okay, and now the system is digitized. To change the maintenance hole numbers, you need to change the structure name. The structure name. Don't change the labels, right? So I'm going to start at the bottom, right? So this structure is actually called manhole 60A. right? So don't touch the label, right? This is the structure label here. I'm going to touch the structure, the actual digitized maintenance hole. Right click and go to structure properties, and this is 60A. So I'm going to call this maintenance hole 60A. Whoops, I want to do that in caps. Maintenance hole 60A. And when I say OK, whoops, 60A, watch what happens in the plan view. The label is going to change. Apply, say OK, and now the label is now manhole 60A. Go to the next one. This one should be 301A. So this structure here, name, structure properties. Make this a little smaller. This should be maintenance hole 301. Whoops. Do that again. Maintenance hole 301A. Change the name of the structure, and then the label will automatically update. You can see the label there, 301A. The next one, this is my first maintenance hole, manhole 1A. Manhole 1A. See it changed the name. And then the next one, this structure is manhole 2A. Again, don't touch the label, touch the structure. Change the structure name, maintenance hole 2A, and then the label will react. So you have to do that for all of them, right? So this is 1, 2, this is 3 and 4. This one's going to be 3. Maintenance hole 3A. Maintenance hole 4A. And then start again here, 5A. Six A and 7A and 8. Maintenance hole 6A. Oops. Maintenance hole 7A, and then finally 8A. Say OK. And there we are. Now, if you want to rotate the label, you can't touch the label. You have to rotate the structure. So if you click on the structure, you'll see this grip. This circle will rotate the structure, which rotates the label. So if you want to be in line with the pipe, snap to the pipe for the angle, and now it's parallel to the pipe. The first one always defaults to the 0 angle of the coordinate system, right? It's parallel to this because there's no previous pipe. The next one will take the angle of the previous pipe. So this label will be parallel to this pipe. And this label will be parallel to this pipe. And this label will be parallel to the previous pipe. But at the beginning, there is no previous pipe. So the default is the 0 angle of the plane. So this last two you might want to rotate. Remember, rotate the structure, not the label. The label will have the same rotation angle as the structure. Same thing here. If you don't like that, grab this and make it parallel to this, right? If you go the other way, it's actually plan readable, right? It'll never show the text upside down, even though you're rotating it 180 degrees. Okay? So you can see. Now, if you don't like the position of it, you can actually grip and take the label and now move it. So you can do that if you want. But the rotation angle is tied to the actual structure. So if you change the rotation of the structure, it affects the rotation of the, if you change the rotation of the structure, just made me a liar. If you change the rotation of the structure, it'll change the rotation angle of the label. But then you do have control over the position. You can grip edit this. But if you change the angle of the structure, it changes the angle of the maintenance hole. Okay, so just something to remember that we did last year. Okay, the other thing you'll see now, if you digitize first, you'll get all the lengths that you need from the drawing, right? You can measure the distance of the traced pipes, right? So you don't need this anymore. Once you've done this, you don't need this circle and the line. You don't need these anymore. Select similar. This is what you traced. I'm just going to make a copy, right? You traced, whoops, copy previous. So if you take this, select similar, and you take this, select similar, right? And you make a copy just so you can talk, right? You traced this. You don't need this anymore, right? You can either delete it or freeze it. Now you've got this digitized version of the system. And you can now read all your lengths to type into your spreadsheet. Okay, the slopes might be wrong by default. I think they're all 1%, right? So all the slopes are wrong, but the pipe sizes are correct based on toggling this from 150 to 200 as required. If you make a mistake with the pipe size, if you make them all 150s by mistake, you can always change it. Suppose you want this to be a 200, you click on the pipe, right click. I hope this works because it wasn't before. Swap the part. So instead of a 150, I want this to be a 200. It should change the size, should change the label. Okay, so if you get the wrong part, just swap it out. Okay, so again, don't change the label, change the actual pipe, and the label will show you what the details are. Okay, the slope, same thing, right? If you change the slope of the pipe, you want this to be 0.5%, you go to pipe properties, and you go to change the slope, right? So 0.5%, apply, say okay, and now you see it changes the label. Okay, so never touch the label. The only time you play with the label is if you're moving it, right? You don't like the position of it, but the details inside the label is coming from the database. Okay. Now, before you draw this in the profile, right, you want to do two things. You want to put everything on the correct layer, and there are 4 layers, right? We discussed this before. For the sanitary, there's a layer for the maintenance hole. There's a layer for all the maintenance holes, right? There's a layer for the maintenance holes. Right, that's one layer. Then there's a layer for the pipe. So this is a different layer. Right, the pipes are on their own layer. I'm just color coding it, right? They should all be red, but I just want to identify each one. Then there's a layer for the text for the maintenance hole. That's a separate layer. And then there's a fourth layer, if I got another color, a fourth layer for the pipe label. So there are 2, for every thing you draw, a structure, there's another layer for the label. For everything you draw a pipe, there's a layer for the text for it. So there's 4 layers. The item and its text. The item and its text. So there, for each system, you're going to have 4 layers. Okay, just like last semester. The maintenance hole should be on a layer. The text for the maintenance hole should be on a different layer. The pipes should be on a 3rd layer, and the label for the pipe should be on a 4th layer. And the name of those, and I don't remember if they're in the drawing or not, the default, they might be. If you go to the layer control, you might see them here. I think they are. Sanitary sewer is by name. So SS sewer, so we go here. See, there's the sewer pipe, so that's one layer. Then there's the sewer pipe, the plan. That's the maintenance hole, that's the maintenance hole text. That's the pipe text. Those are the 4 layers for the sanitary sewer. So instead of SAN, you'll see the code here is a 4-letter designation, right? C dash, those first 4 letters represent sanitary sewer. So this is the convention. I'm using this to name the system, but the layers are going to be sanitary sewer, 4 letters. So that's the sanitary sewer layers. Okay, and you'll see them here, right? SSWR. Plan for the maintenance hole, plan for the maintenance hole text, plan for the pipe, plan for the pipe text. So 4 layers. If you want, like I did on paper, you can color code these, right? You can make the maintenance hole red for now. You can make the text for it. Whoops. You can make the text for it. I made it blue, I think, on paper. You can make the pipe green temporarily. And you can make the text orange, which is color 30. Okay, you can do that, and that way when you place the items on the different layers, you can tell they're on different layers, and then go back and change them all to blue, as to red. So let me do that. I'm going to grab this layer. Right now, everything is on layer 0, right, by default. You can go back now to the sewers. Where are they, the sewers? Sanitary sewers, which is maintenance hole here, these 4 layers. Grab the maintenance hole, select similar, and put it on the maintenance hole layer. Whoops. Put it on the maintenance hole layer. So we're looking for sanitary sewer maintenance hole. So they should be red. Okay, there they are. Then you can take the pipe. They're the only ones on layer 0 right now. So I would do for the sanitary system, and then everything for the storm will come onto the 0 layer, and do this again for the storm. Okay. Don't create the sanitary sewer and the storm sewer and have them all on layer 0. Then you can't use this select similar command. Then it'll grab san and storm together because they're on the same layers. Okay, so this should be on sanitary sewer pipe, sanitary sewer plan pipe, so they should be orange. Oops, they should be green, sorry, the labels will be orange. So then this, select similar. These should be on a layer called maintenance hole text. Oops, sanitary sewer maintenance hole text. They'll come up blue, yeah, and then finally the label's going to come up orange. Select similar, so those are all the pipe labels, and change it to sanitary sewer pipe text. Right? So now you know that everything is on 4 layers. Then you can go back and make sure that they're all red. Or you can keep those colors and make sure that they're all red through the viewport. It's up to you how you want to manage this, right? I like to make them all red. It's up to you what you want to do. Okay, so these 4 layers, they're sanitary. They should all be red. Storm should all be green. Water main should all be blue. Okay, and there's your system. So now you need to draw it in the profile. That's the last piece. Okay, now, when you're drawing this in the profile, and I think I made a mistake already. Remember when I drew it, I had street B as the reference alignment? Well, these pipes on street A, right, think they're on street B right now. So if I click on this pipe in structure, right, you'll notice it says street B. You see that? Street B. So I want to make them all street A, and there's a reason for it. If these are all on street B, this one's the exception because it's on both, right? I'll put this on street A for now, but I'll change it again. This is all street A. So these ones, all of these maintenance holes should be on street A. So they say street B, so I'm going to change it here. Aligned reference name. Will it let me do it here? Maybe not. Might not let me. No, it won't let me do it. So you have to do it through the system. So let's go back, and I know that 4, 3, 2, 1, and everything else existing should be on that system. It should be on street A. So we can change it here under the networks, under sanitary, under the structures. If we look at these items here, so 2, 1, 60, 2, all the way up to 4, I believe. All of these should be on street B. Street A. And the reference for it is here. You can see right here, the reference says street B. I'm going to change them all to street A. Oh, well, let me do more than one. Okay, you may have to do one at a time. So 4, 3, all the ones down here should be street A. I forgot to change this on the fly when I did it. Street A. Street A. So I kind of made a mistake here, but it's a good learning exercise. Now, the reason for that is because depending on which road it's associated with, you're going to get station offset based on the reference alignment that you're connected to. So I want this to be relative to street A, but I want this one to be the station and offset of street B. Right? Otherwise, this, and draw a line from the center, is going to get projected either to here, which is the closest part. I don't want the station of street B and the offset of street B to describe this maintenance hole. I want the station of street A and the offset of street A to describe this maintenance hole. The only exception is the junction, right? This one belongs to both streets. And there's a way of dealing with the dual reference. It has a station on both roads. There's a way of dealing with that in the profile. I'll show you that later. Okay, so let's draw these in the profile, or sorry, let's design the inverts. Okay, and again, this is going to be different for everybody depending on where you drew your last maintenance hole. So we start at the top. Okay, and what we want to do is look at the structure. So the structure, if I go to structure properties, under parts, properties, you're going to see the rim elevation. That's the elevation that comes from the surface roads, right? Right here. This surface roads is giving the top elevation for the rim. So you want to write that down or just remember it. You want to take that number, you want to subtract 2.75, and you want to subtract the pipe size. And the first pipe is a 150. Okay, let's go through that again. I'll show you on a sketch. So if we go back to my hand sketch, so it's 19593. So here's the maintenance hole. Here's the maintenance hole. Here's the pipe. From the structure, I get that the rim elevation is 195.93. Let's just double check. 195.93. Okay. So now I know the minimum cover. I want to subtract 2.75, and I want to subtract the pipe size. A 150 millimeter is 0.15 meters. This all has to be in meters. So that gives me the invert at the start of this pipe. So get out your calculator and do the math. 195.93, subtract 2.75, subtract 0.15, and I get a start invert for that first pipe of 193.03. 193.03 meters. Okay, anybody want to verify that? Double check, make sure the math is right. Stephen, yeah, you should do this in world coordinates, right? When you're doing anything related to the Civil 3D databases, you should always be in world coordinates, okay? Sometimes it matters and sometimes it doesn't, so I would always err on the side of caution, make sure you're in world coordinates. Okay, so you might not use this number. If your maintenance hole isn't in the exact same spot as my maintenance hole, or if your profile is different than mine, then you're not going to get the same number, but you're looking at approximately 193-ish. Okay, but yet be exact, use the number from your design. So then I go to this pipe, I go to this first pipe, I right click, and I go to pipe properties. I find the start invert, which is right here. So I'm going to type in 193.03. I'm going to hit enter, and I'm going to calculate. It's going to change the slope. Okay, I want to keep the start. So now I want to change the slope, hold the start. So I want to type my slope in here. I know it's -1. I'm going downhill. When I hit apply, it's going to keep this number, and it's going to change the downstream invert, the end invert. Apply, and I'm done. So now I know the elevation of the end of this pipe. I need to subtract from this a minimum drop to get the start of the next downstream pipe. So what I like to do is copy this, Control C, and paste it into the next pipe start. Okay, so 192.59. I'm going to go to this pipe here now, right click, pipe property. I'm going to go to the start, make it the same. Okay, now I have to adjust that. Now look at the pipes. What's the difference in pipe size between these two pipes? What's the difference in pipe size? What's the difference between this pipe diameter and this pipe diameter? What's the difference in pipe size? 50, yeah, that's right. So 0.05. What's the minimum drop for straight through for sanitary sewers? What's the minimum drop for straight through? Remember my rule, 369. Yeah, it's 0.03. So this is the drop based on the angle, and this is the drop based on the difference in pipe size. Always use the bigger size. So I want to subtract 5 centimeters or 0.05 meters from this start. So I'm going to go back to my pipes. So I want to take 5 off of here. So I'm going to make this 0, right? 15 minus 0.5 is 0.10, or 10, 0. So I'm going to say apply. So now that inverts there. And now I want to go downstream holding the start. So here now I go minus 0.5. All the rest of the pipes are 0.5, negative. I'm going to hit apply. It's going to keep the 109. It's going to change the end invert. So there's the end invert. I'm going to copy this, paste it into the next pipe, which is this little short person here, right? This little guy. Right click, network pipe properties, paste it into the invert, but I have to adjust this for minimum drop. Back to the drawing. I've got a pipe here and a pipe here. What's the difference in pipe size between these two? 0. What's the difference in inverts based on the change in direction? 0.06. This one's bigger, subtract 6 centimeters. Back to the pipe, subtract 6 centimeters, so 65 minus 6 is 59. Apply. Hold the start, negative 0.5. Apply, the 59 remains. I've got an end, which is the start of my next pipe, less the drop. Control copy, say OK, go to that little pipe, right click, network. Oh, that's what I did. Go to the next one. Go to this one. Pipe properties. Paste into the start. Calculate. What's the drop here? It's going to be the same. So I'm going to take 52, subtract 6 is 46, right? 52 subtract 6 is 46. Apply. Minus 0.5, hold the start. It's going to keep that. It's going to change this. And there is the invert of the next pipe. 191.158. So that, let's go back to here. So now I've got, I know the invert here. And I'm going to just write that down so I don't get confused. I want to go back to here. The start is 191.158. 191.158. Okay, I'm going to stop there. I'm going to go back and start over here again. Sorry, can't see what I'm talking about. Right, so I know the invert here now. Okay, before I continue downstream, I'm going to stop and I'm going to start here and go to here and figure out what this invert is. And then between this number and this number, I'm going to calculate the next one. Okay, so I'm going to go back. I'm going to stop there. I've made a note of that invert. This end of pipe, I want to do the same for this. So let's go back. Back to the drawing. Okay, so I've finished designing this pipe. I'm going to wait now. I'm going to start back here. Next thing I want to do is get the rim elevation for this one. So structure property. The rim elevation is right here. So take that, 195.590. I'm going to subtract 2.75. And I'm going to subtract 0.15, the pipe size, 150 millimeters. And I get, anybody? What's the start invert of this pipe? Subtract 275, subtract 0.15. What should we use as the start of this pipe? Somebody want to confirm that? Anybody else? Again, to get the most out of what I'm showing you, you need to do the work. You need to practice. So if you're crunching your calculators, that's awesome. If you're just watching, you can stand on the sidelines as long as you want, but until you do the work yourself, you're not going to get the hang of this. Okay, so yeah, so Zario, you're good. So I'm going to use that. So I'm going to go to this pipe, right click, go to part properties, change the start to 192.69. I'm going to apply, and I'm going to hold the start and go down at 1%. This is the first pipe at 1%. Apply. I'm going to take this end invert, copy, and paste it into the next pipe, which is this one. Pipe properties, and I'm going to paste it here, and I need to have a minimum drop. So what am I going to use for a minimum drop? What's the difference in pipe size for these two? So this is a 150, this is a 200. What's the difference in pipe size? Yep, 0.05. And what's the minimum drop required across here, straight through? 0.03. Use the bigger one, so subtract 5 centimeters. So I'm going to take this and subtract 5. So 81 subtract 5 is 75. Sorry, 76. Apply. Hold the start. I'm going to go down at negative 0.5%. Apply. Now I have an end of this pipe. I'm going to copy it. 191.332. If we go back to my sketch, this invert is 191.332. Okay, so now I need to do this twice. How do I get from here to here? There's two ways. Change in direction, change in pipe size. How do I get from here to here? Change in direction, change in pipe size. Whichever one is lower is going to govern, because I have to be lower than both pipes, so the lower pipe governs. So what's the change in pipe size here? This is also a 200, so 0. And the change in direction, drop requirement? 90 degrees. So I want to subtract 0.09 from this invert to get this. And now I'm going to stop and analyze the other side. How do I get from here to here? Well, the difference in pipe size is 0. Straight through is subtract how much? If I go straight through, so I want to subtract 0.03 straight through. So now this invert from this side should be 191 point, subtract 3 is 302. Whoops, sorry, I'm off screen. Write that down here. 191.302, right? I'm subtracting 3 centimeters. This one I'm subtracting 9 centimeters from 15. 191.15 minus 9 is 068. This number and this number, which one's lower? This one is lower. That's the start of my next pipe. So I'm going to use 191.068 for this start of pipe. 191.068. Apply. Hold the start, negative 0.5. Apply. Now I have the end of this pipe. Control copy, paste it into the next pipe. This little pipe here. Pipe properties, paste it here. I need to adjust it. Same size of pipe, so it's 0, and it's 45 degrees. I'm going to subtract 6 centimeters. So 90 subtract 6 is 84. Apply. I'm going to go down at negative 0.5. Apply, and that's all my pipe invert design. There's one more to do, and I'm going to actually determine the values of the inverts and the slope based on it's an existing pipe. So let me show you that. So I'm not designing these inverts for this existing piece. It's already in the ground. So now I want to look to ledger way to find this invert, and I'm going to go whatever the slope is. Okay, so let's go look at ledger way. So I'm looking at this maintenance hole 60. There's 3 inverts in that maintenance hole. I want the one that goes, if you look at the north arrow, I want the one that goes to the, in this direction, which is southwest. So look at that maintenance hole for sanitary, which is this one here, 60. Sanitary here, right? I want the southwest invert, right? It's the highest one of the 3. And if you look at the graphic, you'll see that. This is the outgoing pipe, this is the incoming, but this pipe and this pipe is on ledger way. That little ellipse, that's the pipe coming out of the subdivision we're designing. So that invert is, according to the sanitary system, 190.525. 190.525. So I'm going to go back to my drawing and go to that pipe, pipe properties. The end of this pipe is 190.525. 190.525. Say, I'm going to apply it. And what's the slope of the pipe? Well, that's in the drawing as well. It's in the plan view. The slope of this pipe is 0.5%, and it's going up into the subdivision, right? 0.5%. So then I'm going to hold the end of the pipe. I'm going to hold the end because I don't want to disturb the 190.525. This is 0.5%. Say apply. And now it keeps this and it calculates the start. And now I can say OK. So now all the pipes that I've digitized have the correct invert. All right, I'm going to save my drawing. Now I simply need to draw them from plan to profile. And to do that, be careful. You don't want to select similar. Okay, I only want the ones on street A on the street A profile, and I only want the ones on street B on the street B profile. So you have to select them one at a time. Or select them all and deselect the other. It's up to you how you want to do it. So I want all the maintenance holes. I want all the pipes, but not the ones on street A. So now I'm going to hit Shift, and I'm going to pick everything on street A, and it'll deselect them. Shift and deselect. Okay, I don't want this one. I don't want any of these, but I do want this maintenance hole. Right? So all the maintenance holes and pipes on street A are selected. And I'm going to right-click, draw parts in profile, and I'm going to go to street B. And it's going to draw the pipes in the profile. Let me go to my plan view and rotate them. So there's all my design. The first one is 1%, the rest are 0.5%. You'll see this one's a little bit smaller than this one, and the obverts match. If I grab this, they should both move, or very close to it. This one and this one are almost the same. Yep. Okay, so now you need to put those on one layer, right? The sanitary profile layer. So select similar, all of these. Go on a layer called sanitary profile. So sanitary sewer profile. Maintenance holes and pipes all together, everything underground in the profile. So there's the pipes drawn in the profile. And then we're also going to look at the other pipes. So now I'm going to grab street A. So select similar, the pipe, select similar, and now I'm going to deselect. Hold the shift key and just deselect everything else. Don't want anything from street B. Do you want that maintenance hole? Because it's on this road as well. Okay, so we'll go to here, right click, add parts to profile, click on street A, and it puts in all the sewers. Notice this one's already red because I drew it once. I already drew it red over here. Again, select similar, put it on the appropriate layer. Sanitary sewer profile. And I've drawn the pipes. And now you need to add the labels and so on. Now, because this is one network, remember, I don't have a sanitary network for street A and I don't have a sanitary network for street B. A nice little cross-reference occurs. Let me show you that. Remember that maintenance hole that's common to both, this one? That's drafted on both profiles. When you draw the pipe in the profile, you don't see it in the maintenance hole. If you don't draw a pipe in a profile, then it shows it as if it's connected at 90 degrees. And let me show you what I mean. So in this profile, I drew this pipe and I drew this pipe, but I didn't draw this pipe. So watch what happens in the profile of street A. So right here is that intersection. Look here. I drew this pipe and I drew this pipe, but I didn't draw the pipe on street B, but there it is. It looks like it's connected at 90 degrees. So that ellipse that you see is because there's a third pipe not drafted in the profile. If you go to the other street, let's go to the plan view. I drew this pipe, but I did not draw this one, and I did not draw this one. So when you look at the profile of street B, you should see this pipe's profile, but two ellipses representing these two connected at 90 degrees. And let's look at that, which is right at the end of street B. Here's the pipe profile on street B. You should see two ellipses in the maintenance hole. And there they are. They're cross-referenced. And it's dynamic. If I change the invert of either of the pipes, these ellipses, just like the pipe, will change, right? If I lower this, if I bring this way down here, right? See that difference there? Watch on the other street. It's all the way down here now, right? These two are still high, but this one's low now. So it's dynamically linked. And not only is it dynamically linked for the graphic, but the label, right? Let's put in a label. If I put in a label for this, add label, and don't use this ugly label, change it to the profile label style. And it gives you all the data you need for the profile. Remember this should look familiar. All of these inverts come from the database. The name of the structure, the size, the top elevation, this comes from the road surface right there. This comes from the road surface. This comes from the alignment that the structure is associated with. So in this case here, this is street B. This is the station value of street A. See how small it is? Look at the station. It should be 600 and something. But it's showing the station value for this maintenance hole on street A. This one. Let's add this label. And let me show you the information. I'm going to just match the style. Right? This says station 47, which is about right? 40, 47, in and around here. So the station in the label is associated on street A, but not with street B. Why is it showing the street A label with the street B drafted version? And you can change that. Watch, change. You can click on the label and change the reference for this particular one. Yeah. So actually, you can do the label properties, I believe, and change the. Hang on, there's a way of doing it. Just a second. I want it to say 600 and something, right? So hang on, if I remember how to do this. Label properties. Where's the? Oh, reference alignment. Instead of street A, use street B. And now you have 600 and something. So even though the structure is still associated with street A, I can change the label to the other road if I want. So everything is the same except the station. On this road, it shows it as 621, which is correct. And on this one, it shows it as 47. The structure itself is always associated with street A. But the label now, the label for this one, because it's drafted in B, can be changed. You can change the reference. And that's a pretty powerful tool. So you can see now, the reason that these two show up is because it's one network. I don't have a sanitary system for one road and a different pipe network for the other road. I don't have a street A sanitary and a street B sanitary. I just have sanitary. And because they're all part of one database, it does this neat little thing where it knows if you don't draw the pipes, you see them as if they're connected at 90 degrees. And you can actually look at this. Watch. If I delete this pipe, watch the two maintenance holes. I'm not deleting the pipe, I'm deleted the drafted version of it, right? So watch, if I erase this, watch the two maintenance holes. It thinks that pipe's connected at 90 degrees. So if you're not drawing the pipe, it draws the ellipse. If you draw the pipe, then you don't see the ellipse. And that's very powerful. Okay, so now you need to put in all your labels for the sanitary maintenance holes. And then there's a label for your for the pipe. Change this. This is ugly, right? Change it to profile. Not standard, but profile, and it gives you all the data you want. And again, these labels, select similar, the labels for the sanitary, whether it's a pipe or a maintenance hole, needs to go on the profile text. Sewer profile text. Okay. So in the plan view, there's 4 layers. Maintenance hole text, pipe text. In the profile, it's either the stuff, maintenance holes and pipes, all together on one layer, and the labels, whether it's a pipe or a maintenance hole, all on one layer. Okay, so I'm pretty much done my design, right? Except I don't have all the labels. If you bring in all the labels, don't waste time moving them around until you bring in your storm sewer. And then you can manipulate, make sure that the labels aren't on top of each other. Because you don't want to move these and then overwrite them with the storm and have to move them again. Okay, that's some advice I gave you last semester. Okay, I haven't done it yet, but I need to do my design sheet. I still have to prove the calculations, that all the pipe sizes have the capacity for the expected flows. Okay, so that's plenty of work for next week. The good news is you can do whatever you want. You can do the pipe drafting first, because those sizes and slopes aren't going to change, or you can do the spreadsheet first. Right? It's kind of chicken and egg. You do one or the other first, and then vice versa. The storm sewer is not so. You must do the storm sewer sheet first to get your sizes and slopes, and then you draw your solution. And we'll cover that next week. So I know that was a long lecture today with a lot of theory, with a lot of drafting, and so on. Again, this whole thing is recorded. It might take a while to compile. You may not see it until late tonight or tomorrow morning. For homework, and remember, when I teach you something, everything I've taught you today, I expect you to do for next week. That way it's done. And then we can move on to the next thing. Okay, so I think splitting up sanitary with storm, and storm is a little more complicated, is a good place to stop. So we're not talking storm today at all, right? For homework, draw your sanitary sewers in plan and in profile, design all your inverts, and do the spreadsheet. You have a week to do that. Get that ready, and then you can do your storm design. The storm is a lot more complicated. We'll cover all that next week. Okay, but this is a good way to kind of, dip your toe in the water to see, whether you understand this stuff. This is a good way to warm up because the storm's more. The Excel spreadsheet, I think Professor Neruzzi posted those. Let me just check. Usually he posts them, but I will double check. Let me just see. So if you go to the course MED and you go to course documents, he has he given you the spreadsheet? I think I gave them to you already. Let me just check. If we go to project files, I'm not sure that he did. Let me just check one more time. Documents. Where is it? So under, let me try this. So the PDFs are there from the original subdivision, but not the Excel sheets. Not the Excel sheets. So I'm going to post the Excel sheets, the blank sheets. I'll do that in the next half an hour or so. So I don't think they're there. Usually he gives them, but I'll provide them. Where are we? Sorry. Yeah, so Brian, I made it by importing from Adobe into Excel. Okay, I'm going to give you the Excel temp sheet though. I'll give you the Excel template for sand and storm. Okay. They'll be blank, like there's no formulas, right? You'll just see, like, if we go back to here. Anyway, I'll post them. Okay, I'll put them in. Remember, all my stuff is in the project files folder. Professional usually posts all his files. I've got a folder. It's red text called project files. I'm going to put my stuff in there. Okay, so I don't know why we didn't separate mine and his, but I have all of mine in one folder. He has his throughout. So just double check there. Okay, so that's it for today. I know it's a lot, but if you can do this, you're gonna be in the right mindset to do the storm, right? Because it's more of the same plus. Okay, so it'll give you a really good running start to do the storm. All right, I'm gonna stop recording.